What if everything you think you know about space and time is not just incomplete, but fundamentally mistaken? We look up at the night sky and we see a predictable clockwork of stars and planets, a universe governed by rules we believe we understand. But what if the cosmos is far stranger, far more bizarre than our textbooks dare to suggest? Hidden within the vast darkness are riddles, cosmic glitches in the very fabric of reality that defy our most established laws of physics. These are the unexplained anomalies of space-time, moments where the universe seems to break its own rules, presenting puzzles that leave even the most brilliant scientists scratching their heads in wonder and confusion. These aren't just curiosities, they are profound challenges to our perception of existence itself, hints that a deeper, more mysterious layer of reality is waiting just beyond our current grasp. Today, we're embarking on a journey to explore these breathtaking cosmic mysteries. We'll venture beyond the edge of the known into a realm where logic twists and the familiar laws of nature simply don't apply. Imagine the fabric of the cosmos as a vast, shimmering tapestry. For the most part, it's smooth and consistent, but here and there we find strange knots, unexpected tears, and puzzling threads that lead nowhere. These are the phenomena we'll be investigating, events and objects so peculiar that their very existence forces us to question the foundations of everything we hold to be true. They are the universe's way of whispering that there is so much more to learn, that the greatest adventures in human understanding are still ahead of us, waiting in the dark. In this video, we are going to count down 25 of the most utterly perplexing anomalies ever documented. From stars that vanish without a trace to signals from the void that hint at intelligence, from regions where time itself seems to stutter and slow, to cosmic structures so vast they shouldn't be able to exist. Each one is a story, a piece of a grander puzzle that we are only just beginning to assemble. So get ready to have your mind expanded and your perspective shifted. This is not just a list, it's an invitation to look at the cosmos with new eyes, to share in the collective awe and curiosity that drives humanity ever forward into the great unknown. Let's begin. Number 1 on our list begins close to home, or at least within our own solar system, with a mystery that had NASA scientists puzzled for over 30 years. In the early 1970s, humanity was taking its first tentative steps into the outer solar system with the Pioneer-10 and Pioneer-11 probes. These twin spacecraft were pioneers in the truest sense, tasked with the first ever flybys of Jupiter and Saturn before embarking on an eternal journey into the void. For decades, they faithfully phoned home, their faint signals tracked by NASA, a deep space network with incredible precision. But as the years turned into decades, a small, persistent whisper of a problem began to emerge from the complex data. Something was wrong, very wrong. The probes were not where our best calculations, which accounted for the gravitational pull of every known planet and asteroid, said they should be. They were slowing down. This was the pioneer-anomaly, an almost imperceptible but constant deceleration, a tiny, mysterious force acting upon the spacecraft as if space itself had a faint, invisible drag. The discrepancy was about 10 billion times weaker than the gravity we feel on Earth's surface, but over the vast interplanetary distances the pioneers were traveling, that tiny effect compounded into a massive navigational error. By the time Pioneer-10 was billions of kilometers away, it was hundreds of thousands of kilometers off its predicted course. You have to understand, in the precise science of orbital mechanics, this was like a red alert siren blaring in a silent room. The laws of physics, as we knew them, were being violated right in our own cosmic backyard. For years, this tiny blue shift in the probe's radio signals, indicating they were decelerating towards the sun, fueled intense debate and wild speculation. Was there some unknown, diffuse cloud of dark matter gravitationally tugging on them? Could there be a previously undiscovered planet or a swarm of Kuiper belt objects exerting an unseen pull? Some even proposed more radical solutions, suggesting that our understanding of gravity itself was flawed, and that Newton's or Einstein's equations needed modification on a galactic scale. The mystery was a profound embarrassment and a thrilling challenge, a ghost in the machine of our solar system. The ultimate solution, however, turned out to be far more mundane, yet in its own way just as brilliant. After decades of painstaking analysis, a team of researchers managed to recover old telemetry data and construct a highly detailed thermal model of the Pioneer spacecraft. They discovered the culprit wasn't a new force of nature or hidden matter, but something much simpler: heat. The spacecraft were powered by radioactive plutonium, and that decay generated a steady, gentle warmth. This heat was radiated away from the craft, but not perfectly symmetrically. A tiny, anisotropic push, a greater amount of thermal radiation bouncing off the back of the spacecraft's main antenna, was acting like a faint, constant braking engine. Once this thermal recoil force was meticulously calculated and accounted for, the anomaly vanished. The Pioneers were precisely where physics said they should be all along. This story is a powerful lesson in scientific humility. It shows us that even when faced with data that seems to point towards revolutionary new physics, the answer can sometimes lie in the intricate, overlooked details of our own technology. The Pioneer anomaly wasn't a crack in the fabric of reality, but a masterclass in engineering and persistence, reminding us that before we chase cosmic phantoms, we must first be certain we are not simply seeing the reflection of our own creations. If the Pioneer anomaly taught us to look for answers in the intricate engineering of our own probes, then our next mystery serves as a stark reminder that the universe is rarely so accommodating. Just when we thought we had a handle on the delicate dance of orbital mechanics, a new and even more perplexing puzzle emerged, one that occurred not in the deep, silent darkness, but in the fleeting moments when our spacecraft swung past our own planet. This is the flyby anomaly, and for decades it has presented a head-scratching glitch in the gravitational rulebook that we rely on to navigate our solar system. The principle of a gravity assist, or a planetary flyby, is a cornerstone of modern space exploration. It's a masterful trick of celestial mechanics, a way to steal a tiny bit of a planet's orbital momentum to slingshot a spacecraft onto a new trajectory, saving immense amounts of fuel and time. We calculate these maneuvers with breathtaking precision, accounting for the gravitational pull of the sun, the moon, and even the subtle pressure of solar radiation. For the most part, it works flawlessly, but on several notable occasions, something has gone inexplicably wrong, or perhaps mysteriously right. The story truly began to capture attention with the Galileo spacecraft in 1990. Launched to study Jupiter, Galileo needed 2 gravitational kicks from Earth to build up enough speed for its long journey. During its first Earth flyby, scientists watched their tracking data with astonishment. As the probe whipped around our planet, it gained a tiny, unexpected burst of speed. The increase was minuscule, a change in velocity of just a few millimeters per second. But in the hyper-precise world of orbital dynamics, it was a massive discrepancy. Galileo was suddenly moving 4.6 millimeters per second faster than every single physics model predicted. At first, engineers dismissed it as a fluke, an unaccounted-for data error. But then it happened again. The near-Shoemaker spacecraft, on its way to an asteroid, performed an Earth flyby in 1998 and experienced an even larger anomalous boost of over 13 millimeters per second. The Rosetta probe, famed for its comet rendezvous, showed a 1.8 millimeter per second anomaly during its 2007 flyby. Each event was a small but undeniable defiance of physics. It was as if the spacecraft were getting an extra, invisible push from an unseen hand, a subtle nudge that our equations failed to capture. The pattern was clear. During these critical gravitational maneuvers, our understanding of how energy and momentum are exchanged between a planet and a probe was somehow incomplete. So, what could possibly be causing this? The search for an explanation has taken scientists down some fascinating and radical paths. The most straightforward hypothesis points to our own planet. Could our models of Earth's atmosphere, its density at high altitudes, be slightly off, creating an unanticipated form of atmospheric drag or, counterintuitively, a push? Or perhaps our mapping of Earth's gravitational field itself is imperfect, with slight lumps and bumps in our planet's mass distribution imparting these tiny velocity changes. Yet, when these factors are modeled with ever-increasing sophistication, the anomaly stubbornly persists. This has led to more profound and frankly more thrilling possibilities. Some physicists have explored the concept of rotational frame dragging, a phenomenon predicted by Einstein's theory of general relativity. The idea is that a massive rotating object like Earth literally drags the fabric of space-time around with it as it spins. Could this lens-thirring effect be imparting an extra twist of momentum to a spacecraft during a close flyby? Calculations suggest its influence would be far too weak to account for the observed speed changes, but it points to the kind of exotic physics that this anomaly invites us to consider. Other theories venture even further, proposing that dark matter might be clustered around Earth in a way that subtly alters local gravity, or that our fundamental laws of inertia need a slight modification on the scale of the solar system. Unlike the pioneer-anomaly, which was eventually solved, the flyby anomaly remains an open case. It doesn't happen with every spacecraft flyby, which only adds to the mystery, making it incredibly difficult to pin down a single, consistent cause. It's a ghost in the data, appearing just often enough to assure scientists it's real, yet remaining just elusive enough to defy all conventional explanation. Every time a spacecraft lines up for a gravity assist today, a small team of orbital dynamicists watches the telemetry with bated breath, hoping that this might be the flyby that finally reveals the secret, offering a clue that could either be neatly tucked into our existing models or force us to rewrite a fundamental chapter in our book of cosmic rules. But if these anomalies within our solar system hint at gaps in our understanding of local physics, then the next phenomenon we must confront is on an almost unimaginably larger scale, challenging the very foundations of cosmology itself. This is dark flow, and its discovery revealed that entire clusters of galaxies, the largest gravitationally bound structures in existence, are all moving in a coordinated, river-like motion toward a single point on the cosmic horizon, a motion that simply should not exist. The story of dark flow begins not with optical telescopes, but with a satellite designed to stare into the afterglow of creation itself, the cosmic microwave background, or CMB. This faint microwave radiation is the oldest light in the universe, a snapshot from when the cosmos was just 380,000 years old. It fills all of space with a nearly uniform temperature of about 2.7 degrees above absolute zero. By studying tiny fluctuations in this temperature, cosmologists can learn an incredible amount about the universe's infancy, its composition, and its large-scale structure. The Wilkinson Microwave Anisotropy Probe, or WMAP, was launched to create the most detailed map of this primordial light yet. And while it brilliantly confirmed many aspects of the Big Bang theory, it also revealed something deeply unsettling. A team of scientists led by Alexander Kashlinsky was analyzing the WMAP data, looking for a specific kind of imprint. Their method relied on the Sunyaev-Zeldovich effect, a subtle distortion that occurs when the hot gas in a galaxy cluster scatters the CMB photons passing through it. By studying this, they could measure the velocity of these enormous clusters relative to the overall expansion of the universe. The expectation was that these motions would be random, a chaotic jostling of cosmic structures as they were pulled by the gravitational forces of their neighbors. What they found was anything but random. To their astonishment, they detected a startlingly coherent stream. Hundreds of galaxy clusters spanning billions of light years were all rushing in the same direction at speeds of over 600 miles per second. It was as if an immense, unseen hand was herding them toward a specific region of space, a point located in the general direction of the constellations Centaurus and Vela. This presented a monumental problem for the standard model of cosmology, which is built upon the cosmological principle. This foundational idea states that the universe, on large enough scales, is homogeneous and isotropic. It should look the same in all directions and have no preferred center or axis. The discovery of dark flow directly contradicts this. It suggests the universe has a tilt, a fundamental lopsidedness on the grandest of scales. The gravitational pull required to cause such a coherent motion would have to come from something truly colossal, something far beyond the edge of our observable universe. But according to our best models, nothing should be beyond that edge that can exert such an influence. The observable universe is, by definition, all that can affect us since the Big Bang. So, what could possibly be tugging on our entire cosmic neighborhood? Theorists have put forward some of the most mind-bending concepts in modern physics to explain it. One leading hypothesis points toward the multiverse. In this scenario, the gravitational pull causing dark flow originates from a region of space-time that is completely disconnected from our own another universe, bubbling in the vast inflationary foam of the multiverse. The fabric of space-time from that other universe could be exerting a gentle but immense gravitational pull on the matter in our own, creating this cosmic current. Another, even more radical idea suggests that dark flow is not a pull from outside but an imprint from before, a relic from the era that preceded the Big Bang. Some cyclic or bouncing universe models propose that our Big Bang was not a true beginning, but a transition from a previous cosmic phase. The structure of that prior universe could have left a gravitational fingerprint that set this vast flow in motion as our own universe was born. Of course, the scientific community remains deeply divided. Skeptics have questioned the statistical significance of the findings and the methods used to subtract the complex background signals. Subsequent data from the Planck satellite, the successor to WMAP, has been analyzed with conflicting results, some supporting the phenomenon and others refuting it. This ongoing debate is a perfect example of the scientific process at work on the frontier of knowledge. Dark flow stands as a potential and profoundly humbling reminder that our cosmic map may be missing an entire continent. It forces us to consider that the universe we can see might only be a small island in a far vaster and stranger metacosmos, whose unseen structures are, even now, guiding the motion of galaxies on a journey we are only just beginning to detect. Just when the vast, coordinated motion of dark flow challenges our view of the universe on the grandest scales, another anomaly strikes at the very heart of our cosmic self-image, suggesting that the universe might not only be lopsided but perhaps in a deeply unsettling way centered on us. This brings us to one of the most philosophically troubling mysteries in all of modern cosmology, the so-called axis of evil, a strange and unexpected pattern etched into the universe's oldest light. To understand why this is so shocking, we need to revisit the cosmic microwave background. This afterglow of the Big Bang is the bedrock of modern cosmology. Its near-perfect uniformity is the strongest evidence we have for the cosmological principle, the idea that the universe has no center and no preferred direction, that it is on large scales the same everywhere. When scientists first mapped the tiny temperature variations in this background radiation, they expected to find a random, Gaussian distribution of hot and cold spots, a cosmic fingerprint with no discernible pattern or alignment. It should look, for all intents and purposes, like a featureless, static-filled television screen, but it doesn't. When the detailed maps from the WMAP and later the Planck satellite were analyzed, researchers made a startling discovery. The fluctuations were not completely random. Instead, they appeared to be subtly aligned along a particular axis, a single great circle in the sky. And even more bizarrely, this axis seems to be curiously correlated with the plane of our own solar system and the ecliptic. This discovery was so unnerving that scientists gave it a dramatic, almost villainous name, the axis of evil. The evil here isn't some malevolent force, but the deeply troubling implication for physics. Finding a preferred direction in the cosmos is like discovering that the fundamental laws of physics work differently if you're facing north than if you're facing south. It hints that our position in the universe might not be nearly as insignificant as we've always believed. The alignment with our solar system's plane is the most provocative part. It raises the terrifyingly simple question, are we in some way special? Is the universe in some faint way centered on or aligned with us? This directly contradicts the Copernican principle, the foundational idea that we do not occupy a privileged place in the cosmos. Naturally, the first and most conservative explanation is that this is all a grand illusion, a statistical fluke, or more likely, a systematic error in how we process the data. The main suspect is what's known as foreground contamination. Our view of the pristine CMB is muddied by the dust and gas within our own Milky Way galaxy. Scientists must meticulously subtract this foreground emission to see the true cosmic signal. It is entirely possible that our models for this subtraction are imperfect, and that we are inadvertently leaving behind a faint imprint of our own galaxy's structure, which just happens to align with the solar system. This is the explanation most cosmologists fervently hope is true, as it would preserve our standard model of the universe. However, despite years of effort and increasingly sophisticated data analysis from the Planck mission, this mysterious alignment has stubbornly refused to be completely washed away. It persists at a low statistical significance, not strong enough to claim a definitive discovery, but just strong enough to remain a persistent, nagging worry. This has led to more radical proposals that venture beyond simple errors. Some theorists have explored the possibility that this alignment is a real physical effect, a relic from the earliest moments of the universe. One fascinating idea involves the concept of cosmic topology, the overall shape of space-time itself. Could the universe be finite and have a complex, multiply-connected shape like a hall of mirrors? If so, light could wrap around the universe, and we might be seeing multiple images of the same large-scale structures, creating an illusion of alignment. Another, even more profound theory suggests that the axis of evil could be a pre-Big Bang relic. In certain models of the cosmos, like conformal cyclic cosmology, the universe undergoes endless cycles of expansion and contraction. The alignment we see could be a faint gravitational whisper, a scar left on the fabric of space-time from a universe that existed before our own, its structure imparting a preferred direction to our newborn cosmos. Ultimately, the axis of evil remains in a state of scientific limbo. It is not confirmed enough to force a paradigm shift, yet it cannot be entirely dismissed. It stands as a ghost in the machine of cosmology, a subtle pattern that whispers a heretical question. What if the universe, in its most fundamental structure, is not entirely indifferent to us? It challenges our deepest assumptions about randomness and our place in the cosmos, ensuring that every new map of the cosmic microwave background is scrutinized with a mixture of hope and trepidation, as scientists search for the clue that will either finally lay this ghost to rest or force us to completely reimagine our cosmic home. From the subtle, unnerving alignment of the axis of evil, we now turn our attention to a far more forceful and tangible anomaly, one that is actively pulling our entire galactic neighborhood through the cosmos. For decades, astronomers have known that our Milky Way galaxy is not drifting in isolation. It is part of a relentless, coordinated rush through space. This motion, measured with increasing precision, pointed toward a singular, immense gravitational source hidden behind the central bulge of our own galaxy. in a region notoriously difficult to observe known as the zone of avoidance. This mysterious focal point was dubbed the Great Attractor, and it represents one of the most significant gravitational puzzles in our local universe. The story of its discovery begins with the mapping of cosmic velocities. By measuring the redshifts of galaxies, how their light is stretched as they move away from us due to the universe's expansion, astronomers can create a three-dimensional map of their motions. When they did this for our local supercluster, a structure called Laniakea, they found something remarkable. Instead of all galaxies simply receding from each other in a uniform Hubble flow, our Milky Way, along with the entire local group of galaxies, is moving at a staggering speed of over 600 kilometers per second toward a specific spot in the constellation Centaurus. The gravitational force required to orchestrate this vast cosmic river of galaxies must be colossal, equivalent to the pull of tens of thousands of Milky Ways. Yet, when astronomers looked in that direction, they saw almost nothing. The plane of our own galaxy, thick with gas, dust, and stars, completely obscures our view, creating a blind spot that covers a significant portion of the southern sky. For a long time, the true nature of the Great Attractor remained shrouded in this cosmic fog, a ghostly titan whose presence was felt but not seen. The mystery only deepened with further investigation. As observational technology advanced, particularly with X-ray and radio telescopes that can peer through the optical murk of the zone of avoidance, astronomers began to piece together the structure behind the veil. They discovered that the Great Attractor isn't a single, unimaginably dense object. Instead, it is the gravitational heart of the Laniakea supercluster, a massive confluence of galaxies centered on the Norma cluster. This region, while incredibly dense, still didn't seem to possess quite enough visible mass to account for the tremendous pull we experience. This suggested that the Great Attractor itself is likely being pulled by something even larger and more distant, a concept that leads us to the immense Shapley Attractor, a colossal supercluster of galaxies hundreds of millions of light-years beyond. So, the Great Attractor is not the final destination, but a major waypoint in a much longer cosmic journey. But the story of our galactic motion has another, equally fascinating side. For every pull in nature, there is often a complementary push. This brings us to the sixth anomaly, a concept that completes the picture, the Dipole Repeller. For years, cosmologists struggled with a nuanced aspect of our motion. While the Great Attractor pulls us toward Centaurus, the precise magnitude and direction of our velocity couldn't be explained by pull alone. A team of researchers proposed a radical and elegant solution. What if we are not only being pulled from one direction, but also being pushed from another? Their models suggested the existence of a vast, extraordinarily empty region of space, a cosmic void located in the opposite direction from the Great Attractor. This is the Dipole Repeller. The physics behind this push is a direct consequence of the universe's expansion. Imagine space itself as a stretching fabric. In regions crowded with galaxies and dark matter, gravity acts as a brake, slowing down the expansion. In stark contrast, in an immense void where matter is scarce, there is very little gravity to counter the overall stretching. As a result, these underdense regions expand faster than the cosmic average. From our perspective, sitting in a relatively denser part of space, it appears as if this fast expanding void is effectively pushing us away. It's not a force in the traditional sense, but a kinematic effect of relative expansion. We are, in a way, sliding downhill away from the emptiness. The Dipole Repeller is this hypothesized void, and its proposed location aligns perfectly to provide the necessary push that, when combined with the pull of the Great Attractor and the more distant Shapley supercluster, accurately explains the observed velocity of our galaxy. Together, these two anomalies present a dynamic and balanced cosmic tug-of-war. Our journey through the universe is not dictated by a single monstrous source of gravity, but by the intricate interplay between the dense knots and the vast deserts of the cosmic web. The Great Attractor represents the pull of overwhelming mass, a gravitational beacon hidden in plain sight. The Dipole Repeller represents the push of profound emptiness, a repulsive force generated not by anti-gravity, but by the relentless and uneven expansion of the universe itself. Their combined influence shapes the trajectory of not just our galaxy, but of countless others in our local volume of space. The enduring mystery now lies in the details of this mass distribution. What is the precise architecture of the dark matter that undoubtedly forms the true skeleton of these structures? And what other immense voids or attractors lie just beyond our current maps, waiting to be discovered and forever altering our understanding of this grand gravitational dance? But just as we come to understand the push and pull shaping our local galactic journey, a far grander and more unsettling realization emerges about our cosmic address. It appears we may not just be moving through a void, we might be living in the middle of one. This is the KBC Void, named for the scientists Ryan Keenan, Amy Barger, and Lennox Cowie, who first compiled the overwhelming evidence for it. Their findings suggest we reside inside a staggering cosmic emptiness, a spherical underdensity so vast it challenges our most fundamental assumptions about the universe's structure. The concept of cosmic voids isn't new. The large-scale structure of the universe is often described as a cosmic web, a magnificent tapestry of galaxy clusters and superclusters intertwined with vast, bubble-like empty regions. Most known voids are on the order of 100 million light-years across. The KBC Void, however, is in a league of its own. Current observations indicate it could be up to 2 billion light-years in diameter, making it by far the largest void ever observed, a true cosmic supervoid. And we are situated remarkably close to its center. Within this immense volume, the density of matter, both the visible galaxies and the dark matter that binds them, is about 20% lower than the average for the universe at large. While that might not sound like a dramatic difference on such a colossal scale, it represents a staggering deficit of mass, a titanic bubble of relative nothingness in the cosmos. The existence of the KBC Void creates a serious tension with the cosmological principle, specifically with the part that demands homogeneity, that the universe should be roughly the same everywhere when you look at large enough scales. A 2 billion light-year underdensity is not just a small statistical fluctuation, it is a gigantic anomaly. The standard model of cosmology, known as lambda cold dark matter, does allow for some variations in density, but a void of this magnitude is an extreme outlier, sitting right on the edge of what the theory predicts as statistically possible. It forces us to confront a deeply unsettling question. Is this simply a 1 in a billion cosmic coincidence, a rare but permissible fluke? Or does our presence inside such a remarkable structure suggest that we do, in fact, occupy a genuinely special place in the universe, a direct violation of the Copernican principle that has guided astronomy for centuries? The implications of this local emptiness ripple outward, potentially affecting some of the most critical measurements in modern cosmology. One of the most significant controversies in astronomy today is the hubble-tension, the puzzling discrepancy between measurements of the universe's current expansion rate, known as the Hubble constant. One method uses the cosmic microwave background to see the early universe and extrapolate forward, while another uses supernova and other standard candles to measure the expansion rate directly in our local modern universe. These two methods yield stubbornly different answers. The KBC Void offers a potential and elegant solution to this puzzle. If we are living in a vast underdensity, the local gravitational environment is different. The pull of matter is weaker here inside the void. As a result, the space around us is expanding slightly faster than the cosmic average, much like the Dipole Repeller effect, but on a truly monumental scale. This means that when we measure the Hubble constant using nearby supernova, we might be getting a locally inflated value, a reading that is accurate for our cosmic neighborhood, but not representative of the true global average expansion rate. Our galactic address inside this supervoid could be systematically biasing one of our most fundamental cosmic measurements. This idea extends even to the great mystery of dark energy. The apparent acceleration of the universe's expansion is inferred from observations that distant supernovae are fainter than expected, suggesting they are farther away in an accelerating cosmos. But if we are in a giant void, the lower density along our line of sight could also make those supernovae appear fainter. The light from them loses extra energy as it climbs out of our deep gravitational well, an effect known as gravitational redshift. Some physicists have argued that a significant portion of what we attribute to the mysterious force of dark energy could, in fact, be an illusion created by our position within this colossal underdensity. This doesn't necessarily eliminate the need for dark energy altogether, but it suggests its inferred strength could be overestimated, and that local cosmic geography must be accounted for before we can truly understand the dynamics of the entire universe. Of course, the scientific debate is fierce. Detecting and precisely mapping a void of this scale is phenomenally difficult, a slow process of counting galaxies in 3 dimensions and constructing ever more detailed maps of the cosmic web. Some large-scale surveys have found evidence supporting the KBC Void's existence, while others have proposed alternative maps of local structure that are less extreme. The key question remains, is this void real and as vast as proposed, or is it a collection of smaller, interconnected voids that only appear as a single giant structure from our particular vantage point? The answer will ultimately come from next-generation telescopes and galaxy surveys, which will map the universe with unprecedented precision, finally revealing the true nature of our cosmic neighborhood. The KBC Void stands as a profound reminder that to understand the cosmos, we must first understand our place within it, and that the most significant anomalies might not be distant, abstract phenomena, but the very space that surrounds our own galaxy. Now, as we contemplate the possibility that our place inside a cosmic void might be skewing our view, we arrive at an anomaly that strikes at the very heart of modern cosmology, a discrepancy so persistent and so precise that it has become the field's most urgent puzzle. This is the Hubble-tension, and it represents a direct conflict between 2 independent, highly trusted ways of measuring the most fundamental number in the universe, the Hubble constant, the rate at which our cosmos is expanding. For nearly a century, we've known the universe is growing larger, with galaxies racing away from each other as the very fabric of space stretches. The Hubble constant, denoted as h0, quantifies this expansion. Think of it as the speedometer for the entire cosmos. It tells us how fast a galaxy is receding from us for every megaparsec of distance between us. Getting this number right is absolutely critical. It allows us to calculate the age of the universe, to understand its past evolution, and to predict its ultimate fate. For decades, astronomers worked to refine this value, assuming that different methods would eventually converge on a single, agreed-upon number. But in recent years, the opposite has happened. The 2 most powerful methods we have for measuring h0 have begun to diverge, and the gap between them is not shrinking with better data, it's widening into a chasm. On one side of this conflict, we have the early universe measurement. This approach uses the pristine snapshot of the infant cosmos, the cosmic microwave background. By meticulously analyzing the tiny temperature fluctuations in this afterglow, as captured by the Planck satellite, scientists can run the cosmic film backward to understand the exact conditions and composition of the early universe. They can then fast-forward this model through 13.8 billion years of evolution, governed by our standard model of cosmology, lambda cold dark matter. This entire calculation spits out a predicted value for the Hubble constant today. The result from Planck is incredibly precise, approximately 67 kilometers per second per megaparsec. This means that for every additional megaparsec of distance, a galaxy moves away from us 67 kilometers per second faster. On the other side, we have the late universe measurement. This method uses what astronomers call the cosmic distance ladder to gauge the expansion rate directly in our local modern cosmos. It doesn't rely on a model of the universe's evolution. It takes a direct measurement using standard candles objects of known intrinsic brightness, like Cepheid variable stars and type Ia supernova. By measuring how bright these objects appear from Earth, we can calculate their exact distance. Then, by measuring their redshift, we see how fast they are moving away. This is a direct, empirical check on the expansion rate right now. Teams like the one led by Nobel laureate Adam Rees have refined this technique to an astonishing degree, using the Hubble Space Telescope to observe Cepheids in distant galaxies that host supernova. Their result is just as precise, and it is unequivocally higher, around 73 kilometers per second per megaparsec. At first glance, a difference between 67 and 73 might not seem like much. But in the world of high-precision cosmology, where uncertainties have been whittled down to just over 1%, this 6-kilometer gap is a 5-alarm fire. It's a discrepancy of 4 to 6 sigma, meaning the probability that this is a simple statistical fluke is less than 1 in a million. The two most trusted rulers we have for measuring the cosmos are giving us undeniably different lengths. One is telling us the universe is a certain age and has expanded at a certain pace. The other is telling us it's significantly younger and has been expanding faster. They cannot both be correct within our current understanding of physics. So, what could possibly be causing this rift? The explanations scientists are exploring fall into 3 broad categories, each more thrilling than the last. The first, and always most conservative, possibility is that of an unaccounted for systematic error. Perhaps there is a subtle flaw in how we calibrate the cosmic distance ladder. Maybe our understanding of Cepheid variables is incomplete, or there's some unknown source of dust that is making distant supernova appear slightly dimmer than they should, thus throwing off the distance calculation. Teams on both sides of the tension have spent years hunting for these hidden errors, cross-checking each other's work, and introducing new standard candles like the brilliant red giants in the TRGB method. Yet the tension not only remains, it has solidified. It persists even when different late universe methods are used, making a simple observational mistake seem increasingly unlikely. This leads us to the second and far more exciting category, unknown astrophysics. Could there be a new ingredient in our cosmic recipe that we haven't yet accounted for? One intriguing proposal is the existence of a new type of relativistic particle, often referred to as dark radiation. In the early universe, these fast-moving particles would have altered the timing of key events, like the formation of the first atoms, leaving a subtle imprint on the cosmic microwave background that would, in turn, change the extrapolated value of the Hubble constant, potentially bringing it into alignment with the late universe measurement. Another idea points back to the KBC Void. If our local cosmic neighborhood is indeed a vast underdensity, then the gravitational landscape here is unique. The expansion rate isn't a single, universal number. It can vary slightly from region to region based on the local density of matter. Our local measurement of 73 might be correct for our galactic vicinity, while the CMB-derived value of 67 represents the true global average. We would then be faced with the fascinating realization that the Hubble constant isn't truly constant everywhere. The third and most profound category of explanation is that we are seeing the first cracks in our standard model of cosmology, lambda CDM. This model, which incorporates dark energy and cold dark matter, has been spectacularly successful for decades. The Hubble-tension might be the first hard evidence that it is incomplete. Perhaps dark energy, the mysterious force driving cosmic acceleration, is not a constant as we've assumed. Maybe it has been evolving over time, becoming stronger or weaker, which would drastically alter the expansion history of the universe and resolve the discrepancy. Or perhaps our understanding of gravity itself, enshrined in Einstein's theory of general relativity, needs to be modified on cosmic scales. These are not small adjustments. They would require a fundamental rewriting of the textbooks, a new chapter in physics that incorporates something beyond our current best theories. The resolution of the Hubble-tension is one of the most pressing goals in all of science. New observatories like the James Webb Space Telescope are now turning their powerful gaze toward this problem, aiming to measure the cosmic distance ladder with unprecedented accuracy, free from the calibration uncertainties that plagued older telescopes. The fate of our cosmic model hangs in the balance. Will a hidden systematic error finally be found, bringing relief to a generation of cosmologists? Or will the discrepancy hold, forcing us to accept a more complex, more dynamic, and ultimately more mysterious universe than we ever imagined? The answer will not just change a number in a textbook. It will redefine our very understanding of cosmic evolution, from the first spark of the Big Bang to the distant future of all that exists. Moving from the grand-scale tension in the Hubble constant, we encounter a mystery that strikes at a much more elemental, yet equally profound level. This is the cosmological lithium problem, and it transports us back to the universe's very first minutes, to a fleeting era known as Big Bang nucleosynthesis. During this explosive period, when the entire cosmos was a seething, dense soup of fundamental particles, the first atomic nuclei were forged. The theory governing this process is a masterpiece of predictive power, calculating with stunning accuracy the primordial abundances of the universe's lightest elements. It perfectly predicts the amount of hydrogen and helium we observe throughout the cosmos. But for one particular element, the theory breaks down spectacularly. The universe contains only about 1/3 of the lithium-7 that our most sophisticated models insist should be there. It's as if the cosmic recipe for creation called for 3 cups of lithium, but we can only ever find 1. To understand why this is so baffling, you have to appreciate the elegance and precision of Big Bang nucleosynthesis. For a brief window from about 1 second to 20 minutes after the initial singularity, the temperature and density of the universe were just right for protons and neutrons to begin fusing together. This period created almost all the universe's primordial hydrogen, its deuterium, most of its helium, and a tiny trace of lithium. The calculations that predict these abundances are not rough estimates. They are exquisitely sensitive to the conditions of the early cosmos, such as the density of ordinary matter and the number of types of neutrinos. The fact that the predicted and observed amounts of deuterium and helium align so beautifully is a cornerstone of the Big Bang theory. That's what makes the lithium discrepancy so glaring. It's not a small, marginal error. It's a factor of 3 mismatch, a glaring outlier in an otherwise perfectly tuned symphony. For decades, astronomers have worked to confirm this shortage, measuring lithium abundances in the oldest stars in our galaxy, the so-called population 2 stars that formed from nearly pristine material shortly after the Big Bang. These ancient stellar relics act as cosmic time capsules, preserving the chemical composition of the early universe. And no matter where we look in the atmospheres of these ancient suns, the story is the same. The lithium abundance is consistently and significantly lower than the Big Bang model predicts. This isn't a problem of modern contamination or galactic chemical evolution. It's a fundamental inconsistency written into the oldest stars we can find. The universe, it seems, started its life with a lithium deficit. So, where did the lithium go, or was it never made in the expected quantities to begin with? Scientists have pursued explanations along 2 main paths, the nuclear physics route and the exotic physics route. The first line of investigation questions whether our understanding of the nuclear reactions themselves is complete. The chain of fusion that leads to lithium-7 is complex, involving the production of a fragile isotope of beryllium. It's possible that there are unknown or poorly measured nuclear reaction rates at play. Perhaps lithium-7 is being destroyed by nuclear pathways we haven't yet identified, maybe through interactions with yet unmeasured resonant states of nuclei that would have provided a more efficient destruction channel in the hot early universe. The challenge here is that these nuclear cross-sections are incredibly difficult to measure in laboratories on Earth, requiring conditions that replicate the inferno of the Big Bang itself. While ongoing experiments at particle accelerators continue to refine our knowledge, a simple nuclear solution has remained elusive. This leads to the second, far more thrilling possibility, that the lithium problem is a sign of new physics. Could something beyond the standard model of particle physics have been active during those first few minutes, subtly altering the nuclear chain? One compelling idea involves exotic particles like supersymmetric particles or actions. If such particles existed, they could have altered the balance of the early universe in a crucial way. For instance, if a new, weakly interacting particle decayed during or just after Big Bang nucleosynthesis, it could have injected extra energy, increasing the density of photons relative to baryons. This would have shifted the freeze-out point for neutrons and protons, subsequently changing the yields of all the light elements, potentially suppressing lithium production without ruining the excellent agreement for deuterium and helium. Another radical proposal suggests that these exotic particles could have directly destroyed lithium nuclei through interactions that standard physics does not allow. The lithium problem, therefore, becomes a potential window into the dark sector of the universe, a hint that particles we are now hunting in giant underground labs and particle colliders were actively shaping the cosmos from its very first moments. Ultimately, the cosmological lithium problem is a stark reminder that our understanding of the universe's birth, while remarkably successful, is not yet complete. It's a small anomaly with massive implications, a nagging detail that suggests a chapter is missing from the story of creation. Whether the answer lies in a refined nuclear reaction rate discovered in a terrestrial lab, or in the discovery of a completely new type of particle, resolving the lithium discrepancy will undoubtedly lead us to a deeper, more nuanced picture of those first explosive minutes of everything. It stands as a testament to the power of a single, stubborn day, a point to challenge our most fundamental theories, pushing the boundaries of cosmology and particle physics in the quest to understand why the universe turned out just the way it did. And so we come to an anomaly of a different kind, one that did not emerge from the depths of cosmological data or the silent motion of galaxies, but from a single, electrifying burst of sound, a shout in the dark that lasted for just 72 seconds and then vanished forever. This is the story of the WOW signal, an event so stunning to the astronomer who discovered it that he simply circled the alphanumeric code on the computer printout and, in a moment of pure, unadulterated astonishment, scrawled WOW. In the margin, it remains to this day the most compelling, tantalizing, and utterly mysterious signal ever detected in the decades-long search for extraterrestrial intelligence. The stage for this cosmic drama was the Ohio State University's Big Ear radio telescope, a sprawling, stationary array that scanned the sky as the Earth rotated. On the evening of August 15, 1977, this giant electronic ear was listening on a frequency very close to 1420 MHz. This specific frequency is not random. It lies within a uniquely quiet band of the radio spectrum known as the water hole, a region where background noise from the universe is naturally minimal. It's also a frequency that is scientifically significant, being emitted by the hydrogen atom, the most common element in the cosmos. For decades, SETI scientists had postulated that this would be a logical, hailing frequency, a cosmic channel on which an advanced civilization might broadcast its presence, knowing that any listening astronomers would understand its universal importance. And on that quiet summer night, Big Ear heard something. The signal that registered was a narrowband radio transmission, a sharp, pure tone. This characteristic is crucial. Natural astrophysical phenomena like pulsars or quasars produce broadband radio noise, a chaotic hiss across a wide range of frequencies. The WOW signal was the opposite. It was focused, engineered, appearing on only one of the telescope's 50 channels. It also behaved exactly as a signal from a fixed point in space should, growing in intensity for 72 seconds as the Earth's rotation carried the telescope's beam squarely across the source, peaking perfectly in the middle, and then fading away with perfect symmetry as the beam moved on. It was, by every technical definition, the signature we were looking for. The alphanumeric sequence that so amazed its discoverer, Jerry Amon, was 6EQUJ5, a code representing the signal's stunning intensity, so strong that the U stood for a value 30 times higher than the ambient background noise, something the telescope had never seen before. The immediate, heart-pounding question was, of course, where did it come from? The coordinates pointed to a region in the constellation Sagittarius, not far from the globular star cluster M55, a direction largely devoid of nearby stars but rich with the possibility of distant solar systems. The hunt was on. Astronomers around the world, buzzing with the news, pointed their own telescopes toward that same patch of sky, listening intently for a repeat broadcast. They listened for days, then months, then years. The Arecibo dish, the Very Large Array, and countless other instruments joined the search, but the sky was silent. Whatever had spoken that night never spoke again. Not a whisper, not a hint. The WOW signal was a one-time event, a cosmic flash in the pan that has never been replicated. This profound silence forced scientists to search for natural, non-extraterrestrial explanations, and several have been proposed, though each comes with its own significant problems. One of the most discussed theories emerged in 2017, suggesting the signal might have been a reflection from a passing comet. The idea was that the hydrogen clouds surrounding two specific comets, which happened to be in that part of the sky at the time, could have reflected a terrestrial radio signal back toward the Big Ear telescope. While creative, this explanation has been widely criticized by astronomers, including Jerry Amon himself. The frequency of the WOW signal, 1420 MHz, is internationally protected. It is illegal for earthly transmitters to broadcast on it, making a human source highly unlikely. Furthermore, the comets were not actually within the specific area of the sky the telescope was focused on at that precise moment, and the reflection mechanism doesn't adequately explain the signal's clean, narrowband nature and perfect rise and fall pattern. Other natural explanations have fared no better. Could it have been a secret military satellite transmission? Possibly, but no known satellite was in that position, and the signal's fixed celestial coordinates mean its source was not moving with respect to the stars, ruling out any object in Earth orbit. Was it some bizarre, previously unknown form of interstellar scintillation, where the signal from a distant quasar was momentarily focused and amplified by passing through a cloud of plasma? While possible, such events are extraordinarily rare and have never been observed to produce a signal with such a perfect artificial profile. Every proposed natural cause seems to stretch plausibility in its own way, leaving the extraterrestrial hypothesis, while unproven, frustratingly on the table. And that is the enduring power and profound frustration of the WOW signal. It was a perfect candidate in every technical sense, a signal that matched our predictions for an interstellar beacon with uncanny precision. Yet its fleeting, one-off nature denies us the one thing science requires for confirmation: repeatability. It is a data point of one, an anecdote from the cosmos. It stands as a monument to both the promise and the immense challenge of SETI. The universe is vast, and if other civilizations are out there, they may not be constantly broadcasting on all frequencies for our convenience. Their transmissions might be brief, targeted, or simply not meant for us at all. The wow signal is the ghost at the cosmic feast, a reminder that the answer to humanity's oldest question, are we alone, might have been whispered to us once 47 years ago, and we simply weren't quick enough to answer back. It fuels the hope that the next great signal is still out there, waiting for another quiet night, another patient telescope, and another astronomer ready to circle the data and write, wow. Once more, now as we shift our focus from signals that hint at intelligence to the invisible scaffolding that shapes the cosmos itself, we encounter an anomaly that strikes at the very heart of our understanding of the universe's hidden mass. For decades, we've known that dark matter must exist. We see its gravitational grip holding galaxies together, its immense influence guiding the evolution of the largest structures in the cosmos. It is the invisible king ruling the universe from the shadows. But what happens when we try to map the precise domain of this unseen monarch? When we compare our most sophisticated theoretical predictions with the hard, cold data from our telescopes, we find alarming discrepancies that suggest our picture of dark matter is at best a rough sketch. The king's castle, it turns out, may not be built the way we thought. The first of these puzzles is known as the cusp core problem, and it's a tale of two different maps of the same cosmic territory. On one hand, we have our supercomputer simulations which model how cold dark matter, a leading candidate for this mysterious substance, should behave under the relentless pull of gravity. These simulations, which have been remarkably successful on the scale of galaxy clusters, paint a very specific picture of a dark matter halo, the vast spherical cloud that envelops every galaxy. They predict that dark matter should be densely packed at the very center of these halos, forming a sharp cusp where the density skyrockets as you approach the galactic core. It's a natural outcome of how this cold, slow-moving dark matter is thought to collapse under its own gravity. On the other hand, we have the actual observations derived from studying the rotation curves of galaxies, particularly small, faint dwarf galaxies. By measuring how fast stars and gas are orbiting at different distances from a galaxy's center, astronomers can chart the gravitational field and, by extension, map the distribution of all the mass, both seen and unseen. And what these observations consistently reveal is a startlingly different picture. Instead of a sharp, dense cusp of dark matter at the center, the data points toward a large, constant density core. It's as if the very center of the dark matter halo has been scooped out, leaving behind a uniform, almost fluffy distribution of invisible matter. The transition from the expected cusp to the observed core is not a minor detail, it's a fundamental architectural difference. It's the difference between a mountain with a sharp, Matterhorn-like peak and one with a flattened, mesa-like summit. Our simulations build the mountain, reality shows us the mesa. So, what is smoothing out these central cusps? One of the most promising explanations involves a force we are very familiar with: ordinary matter. This idea, known as feedback, suggests that the very processes of star formation and death are powerful enough to reshape the dark matter landscape. Imagine a young galaxy, its center bustling with the violent births and explosive deaths of massive stars. These supernovae unleash phenomenal amounts of energy, blowing vast winds of gas out from the galactic center. As this ordinary matter erupts outward, it creates a powerful gravitational tug of war. The sudden loss of mass from the center causes the gravitational potential to change, and the dark matter particles, responding to this shifting landscape, migrate outward as well, effectively heating up and spreading out to form a smoother core. It's a cosmic game of push and shove, where the dramatic lives of stars can literally carve out the inner sanctum of the invisible dark matter halo. While this is an elegant solution, the challenge lies in the details, modeling whether this process is efficient enough across all types of galaxies to fully account for the widespread lack of cusps remains an active and intense area of research. But the plot thickens with a second, equally troubling dark matter puzzle, the case of the missing satellites. Our magnificent cosmological simulations don't just predict the structure of individual galaxies, they model the formation of the entire cosmic web. And these models generate a very clear prediction. The vast halo of dark matter surrounding a large galaxy like our Milky Way should be teeming with thousands of smaller subhalos, the gravitational seeds for dwarf satellite galaxies. It should be a bustling cosmic metropolis with countless tiny dark matter clumps orbiting our galactic city. Yet when we look up at the sky, we only see a few dozen of these dwarf galaxies. The number has increased dramatically in recent years, with sensitive surveys discovering incredibly faint, ultra-faint dwarfs, but we're still only in the low hundreds, a far cry from the thousands predicted. So, where are all the missing satellites? Have we simply not found them yet because they are too dim? Or is something more fundamental at play? This is where the two problems begin to intertwine. One compelling solution is that the very same feedback processes that may solve the cusp core problem also solve the missing satellites problem. In this scenario, those thousands of small dark matter subhalos did form, just as the simulations predicted. However, in order for a dark matter clump to become a visible dwarf galaxy, it needs to attract and retain ordinary gas to form stars. If the first generation of stars in these tiny protogalaxies was too effective at blowing out its own gas, through those same supernova explosions, then star formation would be snuffed out almost immediately. The result would be a dark matter halo that is completely dark, devoid of any stars for our telescopes to see. These are called dark galaxies, and they could account for the vast majority of the missing satellites. We would be living in a swarm of invisible, starless halos, their presence only detectable through subtle gravitational effects, if at all. These twin anomalies, the cusp core problem and the missing satellites problem, represent a crucial crossroads in modern astrophysics. They force us to ask a profound question. Are the discrepancies simply due to the complex, messy astrophysics of ordinary matter, which our simulations are only now beginning to incorporate with the necessary detail? Or do they point to a more radical conclusion that dark matter itself is not the simple, cold, and non-interacting particle we have long assumed? Perhaps dark matter has a rich inner life. Maybe it can interact with itself through some unknown force, or it possesses a tiny intrinsic velocity that makes it slightly warm, preventing it from collapsing into the dense cusps in the first place. The search for answers is driving a new era of ultra-high-resolution simulations and unprecedented observational campaigns. A grand effort to either complete our map of the dark universe or to discover that the King's true nature is stranger than we ever dreamed. If the silent persistence of dark matter's puzzles reveals a hidden architecture to the cosmos, then the next anomaly we encounter dares to challenge one of the most sacred laws in all of physics, a principle so foundational it feels like a rule of reality itself. This is the bizarre and controversial story of the M-Drive, an electromagnetic propulsion device that seemingly creates thrust from nothing. Imagine an engine with no exhaust, no propellant, no glowing plume of ejected mass. Just plug it in and it pushes. According to Newton's third law, for every action there is an equal and opposite reaction. This should be utterly impossible. It's like trying to move a car forward by sitting in the driver's seat and pushing on the windshield. Yet, for over 2 decades, a handful of dedicated researchers around the world have reported a faint, persistent whisper of thrust from these devices. A whisper that, if real, would represent nothing less than a revolution in how we move through space. The concept was first proposed in the early 2000s by the British inventor Roger Scheuer. His M-Drive, short for electromagnetic drive, was deceptively simple in design. A hollow, truncated copper cone, shaped a bit like a kitchen funnel, sealed inside a vacuum chamber. When you fill this cavity with microwaves, bouncing them back and forth, Scheuer claimed the radiation exerting different pressures on the 2 ends of the cone, greater on the large end than the small end, would create a net force, a thrust in the direction of the larger end. Mainstream physicists were immediately and profoundly skeptical. The law of conservation of momentum is clear. In a closed system, momentum cannot be created or destroyed. For a rocket to move forward, it must throw something backward. The M drive, having no exhaust to throw, appeared to be a textbook example of a perpetual motion machine, a violation of bedrock physics. Yet the tantalizing reports refused to go away. The first major independent test came from a team in China, followed by a group at NASA Eagleworks Laboratory, a small, advanced propulsion research group. Led by scientist Harold "Sonny" White, the NASA team built their own carefully instrumented M drive and tested it inside a vacuum chamber to eliminate any effects from air currents. To the astonishment of many, they reported a small but measurable thrust on the order of a few dozen micronewtons. To put that in perspective, that's about the force a single piece of printer paper exerts on your hand under Earth's gravity, utterly minuscule. But in the frictionless environment of space, such a force, if sustained, could theoretically propel a spacecraft to tremendous speeds over time without the need to carry a single drop of fuel. The key allure was this: an M drive-powered probe could, in principle, travel to Mars in weeks instead of months, or enable deep space missions that are currently impossible due to the tyranny of the rocket equation, which demands enormous amounts of propellant. The scientific community responded with a storm of skepticism and a race to explain the unexplained. The primary and most persistent theory proposed by proponents involves the quantum vacuum. The idea is that the microwaves inside the cavity are not pushing against the copper itself, but against a sea of virtual particles that constantly pop in and out of existence in what we perceive as empty space. In this view, the M drive would have an exhaust. After all, it would be pushing against this ephemeral quantum foam, a concept that bends but doesn't necessarily break conservation laws. However, most quantum physicists dismiss this, arguing that the quantum vacuum cannot be used for propulsion in this way. It's not a medium you can push against. Another, more recent hypothesis suggests that the thrust is not a reaction force at all, but a result of the Unruh effect, a theoretical phenomenon where an accelerating object experiences the universe as a warmer bath of radiation. In this complex model, the microwaves inside the cone could be modifying the inertial mass of the photons in a way that produces an asymmetric force. It's a highly speculative idea that ventures into the edge of known physics. But for every exotic theory, there is a more mundane and often more likely explanation rooted in experimental error. The forces being measured are so incredibly small that they sit right on the threshold of what our most sensitive instruments can detect. This makes them incredibly vulnerable to hidden artifacts. One of the most convincing debunkings came from a team at the Dresden University of Technology in Germany. They built a highly sophisticated, ultra-sensitive torsional balance and tested an M drive with painstaking precision. Their initial results also showed a tiny thrust, but then they introduced a crucial innovation. They ran the experiment with and without a magnetic damper. When the damper was used to cancel out subtle interactions between the device's electronics and the Earth's magnetic field, the measured thrust completely disappeared. Their conclusion was that the apparent thrust was not a new physics phenomenon, but a classic case of measurement contamination. Specifically, Lorentz forces generated by electrical currents in the apparatus wiring interacting with our planet's magnetic field were mimicking the signature of genuine propulsion. Other potential errors include thermal expansion. As the copper cone heats up from the microwaves, it can expand minutely, shifting its center of mass and creating a tiny push that looks like thrust. The M drive controversy perfectly encapsulates the eternal struggle at the frontier of science. On one side, there is the thrilling allure of a potential paradigm shift, a technology that could open the solar system to humanity. On the other, there is the rigid, unforging gatekeeper of scientific rigor, demanding extraordinary evidence for an extraordinary claim. The device sits in a kind of scientific purgatory. It has not been conclusively proven to work under conditions that satisfy the wider physics community, yet the handful of positive results have been just persistent enough to prevent the idea from being completely abandoned. It continues to be a subject of intense online debate and niche research, a ghost of a possibility that refuses to die. Ultimately, the legacy of the M drive may not be a revolutionary engine, but a powerful lesson. It has pushed experimentalists to develop more sensitive measurement techniques and to hunt for subtle sources of error they might otherwise have missed. It reminds us that the path to discovery is often paved with false positives and dead ends, but that the rigorous process of investigating even the most impossible-seeming claims is what keeps science honest and what ensures that when a true revolution does arrive, we will be ready to recognize it for what it is. But if the M drive represents a controversial challenge to classical physics here on Earth, the next anomaly we must confront is one with overwhelming observational evidence, a discovery so robust and universally confirmed that it single-handedly forced us to invent a whole new form of matter. This is the mystery of the galaxy rotation curve, and it begins not with complex theories or futuristic engines, but with the simple, elegant motion of stars around the centers of spiral galaxies, a motion that defies one of astronomy's oldest and most trusted laws. For centuries, our understanding of orbital dynamics was governed by Kepler's laws, principles that work flawlessly within our own solar system. Think of the planets circling our sun. Mercury, the innermost planet, hurtles around at a blistering 47 kilometers per second, while distant, sluggish Neptune plods along at a mere 5.4 kilometers per second. This drop-off in orbital speed with distance is a fundamental consequence of gravity. The Sun's gravitational grip weakens with distance, so objects farther out naturally move more slowly to maintain their orbits. This pattern is known as a Keplerian rotation curve, and for generations, astronomers assumed it would hold true on a much grander scale. That stars orbiting the center of a spiral galaxy like our own Milky Way would behave the same way. The visible disk of stars and gas concentrated in the bright galactic center should provide the dominant gravitational force. Stars close to the center should zip around quickly, while those in the outer reaches, far from the central bulge, should be crawling along. This assumption was shattered by the meticulous work of astronomer Vera Rubin and her colleague Kent Ford in the 1970s and 80s. Using sophisticated spectrographs, they measured the velocities of stars in distant spiral galaxies by observing the Doppler shift of their light. As a star moves toward us, its light is compressed, shifting slightly toward the blue end of the spectrum. As it moves away, the light stretches, shifting toward red. By painstakingly mapping this shift for stars at different distances from the galactic center, they could chart the galaxy's rotation curve. What they found was stunning and completely at odds with Keplerian prediction. Instead of the orbital speeds dropping off in the outer regions of the galaxies, the rotation curves were flat. Stars 10,000, 50,000, even 100,000 light-years from the center were all orbiting at roughly the same high speed. It was as if the entire galaxy, from its bright core to its dim, sparse outskirts, was rotating like a rigid plate, a single solid disk. This was simply impossible if the gravity came only from the stars and gas we could see. The visible matter alone did not have nearly enough gravitational pull to keep those far-flung stars from flying off into intergalactic space. The only logical conclusion was that there had to be more, a lot more. This flat rotation curve was the single most powerful piece of evidence for the existence of dark matter. To explain the constant orbital speeds, there must be an enormous, invisible halo of matter enveloping each galaxy, extending far beyond the visible edge. This halo's mass distribution had to be configured in a very specific way. Its density must decrease in just the right manner so that the total mass within any given radius increases linearly with that radius. This creates a gravitational field where orbital velocity remains constant, perfectly matching the flat curves observed by Rubin and Ford. The dark matter wasn't just a small component, it was the dominant component of the galaxy, the true gravitational engine driving its motion while remaining completely invisible to our telescopes. Of course, such a radical proposal invited alternative explanations, and the most prominent and long-standing of these is known as modified Newtonian dynamics, or MND. First proposed by physicist Mordechai Milgrom in the 1980s, MND offers a very different solution. Instead of invoking unseen matter, it suggests that our understanding of gravity itself is slightly incorrect, but only in the regime of extremely weak gravitational fields, like those experienced by stars in the outer reaches of galaxies. Milgrom proposed a new constant of nature, a tiny acceleration threshold. Above this threshold, Newton's laws work perfectly, but below it, for accelerations so small we rarely encounter them, the force of gravity changes, becoming stronger than the inverse square law predicts. This modification, when applied to galaxy rotation, miraculously produces flat rotation curves without any need for dark matter. For many galaxies, MND provides an astonishingly good fit to the observational data, often better than some early dark matter models. However, MND faces its own profound challenges, particularly when confronted with evidence from larger scales. While it excels at explaining the rotation of individual galaxies, it struggles to account for the behavior of galaxy clusters. When we observe these massive clusters, we can use multiple methods to weigh them. We can measure the motions of the galaxies within them. We can observe how they bend light from background objects through gravitational lensing, and we can measure the temperature of the incredibly hot X-ray emitting gas trapped in their grip. All of these methods consistently point to the same conclusion. There is far more mass present than we can see in stars and gas. MND by itself cannot account for all this missing mass. Its proponents have had to suggest that some form of unseen, non-luminous matter still exists in clusters, perhaps neutrinos with a small amount of mass, effectively reintroducing a form of dark matter, albeit a different kind than in the standard model. Furthermore, the cosmic microwave background, the large-scale structure of the universe, and the bullet cluster, a cosmic collision where the gravitational lensing effect is clearly separated from the visible matter, all provide powerful, independent lines of evidence for a dominant, collisionless dark matter that MND, in its original form, has difficulty explaining. The legacy of Vera Rubin's work is nothing short of a cosmological revolution. She provided the clear, undeniable data that transformed dark matter from a speculative idea into a central pillar of modern astrophysics. The flat rotation curve of galaxies is the anomaly that started it all, the first loud, clear signal that the universe we see is only a tiny fraction of the universe that exists. It forced us to accept that most of the matter in the cosmos is of an unknown form, a substance that does not emit, absorb, or reflect light, yet dictates the motion of stars and the fate of galaxies. Today, the quest to directly detect a dark matter particle is one of the greatest endeavors in science, driving experiments deep underground and observations across the sky. The mystery of the spinning galaxies remains the foundational enigma, a constant reminder that the most profound truths about our universe are often hidden in plain sight, revealed not by what we can see, but by the silent gravitational dance of the stars. Just when we think we have a handle on the grand, sweeping laws of the cosmos, we're often humbled by a paradox that strikes much closer to home, a puzzle that revolves around our own star and its relationship with our ancient planet. This brings us to the faint young sun paradox, a mystery that asks a deeply unsettling question. Why wasn't the early Earth a frozen, lifeless snowball? Billions of years ago, when life was first taking hold on our world, astrophysical models tell us the sun was significantly dimmer, about 30% less luminous than it is today. A star's brightness increases gradually over its lifetime as it fuses hydrogen into helium, increasing the density and temperature in its core. So, back in the Archean eon, around 3 to 4 billion years ago, the solar energy reaching Earth should have been too weak to keep the planet's surface above the freezing point of water. Calculations suggest the average global temperature should have been around -16 degrees Celsius, a deep global glaciation that would have encased the entire planet in ice. And yet, the geological record screams a different story entirely. The evidence for a warm, wet, and crucially, ice-free early Earth is overwhelming and written in stone. We find some of the most ancient rocks on the planet, formations in Greenland and Australia that are nearly 3.8 billion years old, which show clear signs of being shaped by liquid water. These are sedimentary rocks whose very formation requires the erosion and deposition of material in rivers, lakes, or oceans. Even more compelling, we find pillow basalts, distinctive lava formations that only occur when molten rock erupts directly underwater and cools rapidly. Most telling of all are the bands of iron-rich rock known as banded iron formations. These intricate layers of red and black could only have been deposited in oxygen-free oceans, a process that demands vast quantities of liquid water interacting with dissolved iron from hydrothermal vents. There is simply no ambiguity in this geological testimony. The Earth, for its first 2 billion years, had persistent and extensive oceans of liquid water. This presents a stark contradiction: a faint sun but a warm planet. Our climate models, when run with a 30% dimmer sun and our current atmosphere, produce a global icehouse every single time. Something else, something powerful, must have been warming the young Earth, acting as a planetary-scale thermostat to compensate for the solar deficit. The most enduring and widely accepted solution to this paradox points to a dramatically different atmosphere, one dominated by potent greenhouse gases. Our modern atmosphere of nitrogen and oxygen is actually quite thin when it comes to trapping heat, but the early Earth's air was likely a dense chemical blanket. The primary suspect is carbon dioxide. If the ancient atmosphere had hundreds or even thousands of times more CO2 than it does today, the greenhouse effect could have been strong enough to keep the planet comfortably warm. This makes intuitive sense. We know that volcanic activity was far more rampant in the young, hot Earth, constantly spewing CO2 and other gases into the air. However, the geological evidence for such extreme CO2 levels is surprisingly murky. When we look at ancient soils called paleosols and the chemical signatures locked within them, they suggest that while CO2 was higher, it may not have been high enough to single-handedly resolve the paradox. This has led scientists to propose a co-conspirator, methane. Methane is a greenhouse gas that is, molecule for molecule, far more effective at trapping heat than carbon dioxide. On the early Earth, before the rise of oxygen-breathing life, the atmosphere was reducing, meaning it lacked free oxygen. This is the perfect environment for methane, which is readily produced by primitive microbes called methanogens that thrived in the ancient oceans. A small percentage of methane mixed with a background of elevated CO2 could have provided a super-powered greenhouse effect, easily bridging the energy gap left by the faint sun. This methane haze might have given the early Earth a faint orange tint, an alien-looking sky that paradoxically cradled the planet in warmth and made life's first tentative steps possible. There are even more exotic proposals, such as the presence of an ammonia haze, which is also a powerful greenhouse agent, though it is highly vulnerable to being broken down by ultraviolet light. But atmospheric composition isn't the only card nature might have played. Some geophysicists have proposed that the Earth itself was a different world in its rotation. What if the young planet spun significantly faster, resulting in much shorter days? A faster rotation would alter global weather patterns, leading to more pervasive cloud cover. The climatic effect of clouds is complex. Low, thick clouds tend to cool the planet by reflecting sunlight back into space, but high, thin clouds can have a net warming effect by trapping outgoing infrared radiation. If the specific cloud types and distributions on the early Earth were just right, they could have provided an additional insulating blanket. Other theories look to the planet's surface, suggesting that the continents were smaller and more dispersed, leading to a darker global surface with less reflective landmass. A darker planet absorbs more solar energy, which could have contributed a few crucial degrees of warming. The true answer likely lies not in one single mechanism, but in a delicate interplay of all these factors. A thick cocktail of CO2 and methane, a unique cloud regime, and an altered planetary albedo all working in concert to defy the cosmic chill. The implications of solving the faint young sun paradox extend far beyond a curiosity about our own planetary history. They fundamentally reshape how we search for life beyond Earth. Our concept of the habitable zone, the so-called Goldilocks region around a star where temperatures are just right for liquid water, is built on straightforward stellar and planetary physics. But the story of the early Earth tells us this picture is far too simple. A planet that sits outside the traditional habitable zone might not be a frozen wasteland if it possesses a thick, greenhouse-rich atmosphere. Conversely, a planet that sits squarely within the zone could be a frozen ice ball if its atmosphere is too thin. It introduces the powerful concept of planetary climate regulation, where biology and geology actively work to maintain habitable conditions. The Earth itself seems to have a kind of resilience, a buffering capacity against changes in stellar energy. This gives us hope in our search for exoplanets. We should not be too quick to write off worlds orbiting dim, red dwarf stars, for example. If a young Earth could stay warm with a faint sun, perhaps an exoplanet with the right atmospheric composition could do the same, pushing the boundaries of the habitable zone outward and vastly expanding the number of potential cradles for life in our galaxy. The paradox forces a more nuanced view, reminding us that a planet's climate is not dictated by its star alone, but by a beautiful, complex, and sometimes counterintuitive dance between the light from above and the chemistry and geology of the world below. While the faint young sun paradox reveals a hidden interplay between our star and our planet's climate, the next anomaly takes us to the opposite extreme of scale, into the heart of the atom itself. Here, in the realm of the impossibly small, a controversial discovery threatens to upend our understanding of the very forces that hold matter together. This is the mystery of the tetraneutron, a hypothetical particle consisting of 4 neutrons bound together as a single, fleeting entity. According to our most fundamental principles of nuclear physics, such an object should not exist, not even for a fraction of a nanosecond. Its mere possibility strikes at the core of how we think about the strong nuclear force. To understand why the tetraneutron is so heretical, we need to look at how atomic nuclei are built. The universe is built on a balance of 2 fundamental nuclear particles, the proton, which carries a positive charge, and the neutron, which is neutral. The powerful strong force is what glues these particles together into the dense clusters we call nuclei. But this force has a peculiar characteristic: it thrives on balance and pairing. The most stable arrangements involve protons and neutrons working together. We have stable nuclei with 1 proton and 1 neutron, 2 protons and 2 neutrons, and so on. We even have stable systems of 2 neutrons alone, known as dynatrons, within the confines of certain unstable nuclei, but a system of only neutrons. That's a different story entirely. Without the charge-neutralizing presence of protons to mediate the strong force, the repulsive core of the nuclear interaction between neutrons should overwhelm any attraction, making a cluster of pure neutrons instantly fly apart. For decades, every experiment and theoretical model has confirmed this. You cannot have a bound state of 2 free neutrons, let alone 3 or 4. The tetraneutron, therefore, is the nuclear equivalent of a ghost, a specter that logic says cannot be, yet one that some physicists believe they have glimpsed. The first compelling evidence for this phantom particle emerged from a dramatic experiment in 2002. conducted at the Ganil Accelerator in France. Researchers weren't even looking for a tetraneutron, they were studying the properties of unstable nuclei. Their experiment involved firing a beam of unstable lithium-8 nuclei at a target of carbon-12. In a small fraction of these high-energy collisions, the lithium-8 nucleus would essentially strip itself, transferring 4 of its neutrons directly to a beryllium-9 nucleus in the target, creating a highly excited, unstable beryllium-13. This beryllium-13 would then immediately decay, spitting out the 4 neutrons. The key to the mystery lay in what happened next. When the team analyzed the energy and trajectories of these 4 departing neutrons, they found a startling signature. Instead of flying apart independently in a random burst, their data suggested the 4 neutrons were moving in a correlated way, as if they had been momentarily bound together in a single unit, a tetraneutron, that lived for about 10 to the power of negative 22 seconds before disintegrating. It wasn't a stable particle, but a resonant state, a fleeting, quasi-stable configuration that existed just long enough to leave a distinct fingerprint in the debris of the collision. The physics community reacted with intense skepticism, as one would expect for a claim that challenges textbook knowledge. Critics immediately suggested alternative explanations. Perhaps the signal was not a true tetraneutron, but a final state interaction, where the 4 neutrons, while never truly bound, simply interacted with each other very strongly as they were flying apart, creating an illusion of a short-lived particle. Other teams tried to replicate the results, with some finding supporting evidence and others finding nothing. For over a decade, the tetraneutron remained in a state of limbo, an intriguing but unconfirmed anomaly. Then, in 2016, a team at the Riken Research Institute in Japan conducted a more precise follow-up experiment. They used a different approach, colliding a beam of helium-8 nuclei with a helium-4 target. This cleaner reaction also produced a telltale energy signature consistent with a tetraneutron resonance. The Riken results were significant because they seemed to rule out the final state interaction hypothesis more definitively, suggesting that the 4 neutrons really were forming a distinct quasi-bound quantum state, even if it was vanishingly short-lived. If the tetraneutron is real, its implications ripple outward, touching upon some of the most extreme objects in the cosmos. The interior of a neutron star is the ultimate realm of neutron matter, a colossal atomic nucleus the size of a city, comprised almost entirely of neutrons crushed together by immense gravity. Our models of the state of matter in this bizarre environment, known as neutron star matter, are built on our understanding of how neutrons interact with each other. The existence of a tetraneutron or any multi-neutron cluster would suggest that the forces between neutrons are more attractive than we currently believe, especially under extreme density. This could fundamentally alter our equations of state for neutron stars, potentially changing our predictions for their maximum mass, their internal structure, and the nature of the super-dense material at their cores. It might even provide a clue to the behavior of the mysterious neutron poster phases, where nuclei are thought to be squeezed into strange shapes like sheets and tubes. The tetraneutron offers a tiny, laboratory-scale window into the physics of these cosmic giants. The theoretical challenge now is to explain how such a bound state could possibly form. How can the strong force, which seems to reject all neutron systems, be tricked into holding 4 of them together, even for a fleeting moment? Some physicists propose that the answer lies not in the strong force alone, but in a delicate quantum mechanical dance. They suggest the 4 neutrons might arrange themselves in a specific, highly symmetric configuration, perhaps a tetrahedron, where their wave functions overlap in just the right way to create a net attractive potential. It would be an incredibly fragile balance, a house of cards held together by quantum coherence, instantly collapsing if disturbed. Other theories venture into more speculative territory, suggesting that the tetraneutron isn't a traditional nuclear-bound state at all, but rather a manifestation of a new kind of nuclear interaction that only emerges in systems with multiple neutrons. The ongoing debate is a beautiful example of science in action, where a single, stubborn anomaly forces a re-examination of long-held assumptions, pushing both experimentalists and theorists to the limits of their craft in the quest to understand whether this ghost in the machine of nuclear physics is a mere illusion or the first glimpse of a deeper layer of reality. This brings us to an anomaly that strikes at the very edge of known physics, a puzzle involving particles that travel the universe with energies so stupendous they defy our expectations of how the cosmos should behave. We are talking about the GZK cosmic ray cutoff, a theoretical limit that should act as a cosmic speed bump for the most energetic particles in existence, yet one that we have repeatedly observed particles crashing right through. The story begins with the stuff of cosmic rays themselves. These are not rays of light, but atomic nuclei, protons, or the nuclei of heavier elements like iron, that have been accelerated to nearly the speed of light by the most violent events in the universe: supernova, merging black holes, and active galactic nuclei. They constantly rain down on our atmosphere, but the ones that truly stretch our understanding are the ultra-high-energy cosmic rays, each carrying the kinetic energy of a professionally thrown baseball, but compressed into a single subatomic particle. That is an almost unimaginable amount of energy for something so small. Now, in a perfectly empty universe, such a particle could travel for billions of light years unimpeded. But our universe is not empty. It is filled with the faint, cold afterglow of the Big Bang, the cosmic microwave background radiation. This bath of microwave photons is everywhere, a relic from the universe's infancy. And this is where the theoretical limit proposed by physicists Kenneth Greisen, Georgy Zatsepin, and Vadim Kuzmin in the 1960s comes into play. The GZK cutoff is a brilliant piece of cosmic logic. It states that any proton with an energy above about 6 times 10 to the 19th electron volts, traveling over long intergalactic distances, should not be able to reach Earth. Why? Because it would inevitably collide with one of these background photons. But this wouldn't be a simple bump. Due to the incredible speed of the proton, that gentle microwave photon would appear from the proton's perspective as a blistering high-energy gamma ray. The collision would be so violent it would create new particles, specifically a pion, through a process called photomeson production. This interaction acts like a form of cosmic friction, sapping the proton's energy with every collision until its energy falls safely below the GZK threshold. The universe, according to this theory, should have a natural horizon for these ultra-high-energy particles. We should not be able to see them from sources more than about 150 million light-years away. Their energy would be drained over longer journeys. This is where the mystery erupts. Giant observatories like the Pierre Auger Observatory in Argentina and the now decommissioned High-Res and Agosa experiments have been built specifically to catch these rare, ultra-high-energy events. They don't detect the particle directly, but the massive shower of secondary particles it creates when it slams into the upper atmosphere. And the data they have collected is unequivocal. We have detected multiple cosmic rays with energies significantly above the GZK cutoff. We are seeing protons that, according to our best models, should have bled away their energy long before they ever reached our planet. It's as if a marathon runner showed up at the finish line not only without breaking a sweat, but carrying more energy than they started with. These events are not common, but their mere existence is a profound challenge. They are the universe delivering particles that, by all rights, should not be here. So how are these particles cheating the cosmic speed limit? Scientists are exploring several compelling and some truly radical explanations. The most straightforward idea is that these ultra-high-energy cosmic rays are not coming from the distant universe at all, but from relatively nearby sources within our local cosmic neighborhood, within that 150 million light-year GZK horizon. If the source is close enough, the particle wouldn't have had time to interact with enough background photons to lose its energy. The hunt, therefore, is for an incredibly powerful astrophysical engine within our local supercluster. The problem is, when we trace the arrival directions of these anomalous cosmic rays back to their potential sources, we often find nothing. No nearby active galactic nucleus, no brilliant gamma-ray burst remnant, no colliding galaxies that seems powerful enough to be the culprit. This leads to the tantalizing possibility of dead sources, objects like dormant black holes or neutron star mergers that had a single colossal burst of acceleration in the recent past and have since gone quiet, leaving no other trace for our telescopes to find. When local sources fail to provide a clear answer, physicists naturally turn to the possibility of new physics. Could our understanding of the particle interactions themselves be flawed? Perhaps the cross-section for photomeson production is slightly different at these extreme energies than we've calculated. Or, more profoundly, could this be a hint of physics beyond the standard model? Some theories of quantum gravity, which attempt to unite Einstein's general relativity with quantum mechanics, predict subtle alterations in how particles behave at these incredible energies. For instance, special relativity, which underpins the entire GZK calculation, might experience tiny yet measurable violations at such extremes. It's a long shot, but the possibility remains that these ultra-high-energy particles are our first experimental glimpse into a theory of everything, a regime where the familiar rules of spacetime begin to fray at the edges. Of course, we must always contend with the specter of measurement error. Detecting these particles is an indirect and incredibly complex process. The primary particle never reaches the ground. We only see the cascade of billions of secondary particles it creates. Reconstructing the energy and identity of the original cosmic ray from this air shower is a monumental task fraught with potential systematic uncertainties. Could our instruments be overestimating the energy of these events? Teams at the Pierre-Auger Observatory have spent years cross-checking their results using multiple detection techniques. An array of surface detectors combined with fluorescence telescopes that watch the faint glow of the shower developing in the air. Their consistent results have made a simple instrumental error seem increasingly unlikely, solidifying the anomaly as a real feature of our universe rather than a flaw in our detectors. The implications of solving the GZK cutoff problem are as vast as the energies involved. If the solution is astrophysical, it means there are previously unknown or underestimated cosmic powerhouses lurking in our intergalactic backyard, engines of acceleration that defy our current classifications. If the solution is new physics, it could revolutionize our understanding of fundamental forces and the fabric of spacetime. These cosmic rays are messengers from the most extreme environments in the cosmos, and their ability to reach us with such intact energy is a direct telegram, telling us that our map of the universe's most violent phenomena and its most fundamental laws is still missing critical pieces. Each one that strikes our atmosphere is a challenge, a tiny speck of matter carrying a mountain of energy, daring us to explain its impossible journey. Just when we think we've mapped the faint afterglow of creation and found it mostly uniform, the cosmos presents us with a feature so bizarre and out of place that it seems to defy the very notion of a smooth, predictable universe. This brings us to the 17th anomaly on our list, the cosmic microwave background cold spot. Imagine looking at the most detailed map of the infant universe, a snapshot from just 380,000 years after the Big Bang, and finding a single, colossal blotch of cold, a region so vast and so much colder than its surroundings that it stands out like a cosmic bruise. This isn't a small statistical fluctuation. It is a Grand Canyon of cold etched into the fabric of space-time, a structure so large it spans nearly 2 billion light-years across, potentially making it the single largest individual feature in our entire observable universe. The discovery of the cold spot came from meticulous analysis of the data from two spacecraft that have become legends in cosmology. First, the Wilkinson Microwave Anisotropy Probe, or WMAP, and later the Planck satellite. These missions mapped the cosmic microwave background with breathtaking precision, revealing the tiny temperature variations that are the seeds of all future structure, the galaxies and clusters we see today. Most of these variations are small, random, and Gaussian, just as the standard model of cosmology predicts. But the cold spot is different. Located in the constellation Eridanus, it is a coherent, circular area where the temperature dips by about 70 microkelvin below the average. While that sounds minuscule, its size and coherence are what make it extraordinary. The statistical significance is staggering. The probability that such a large, cold feature would appear purely by chance in a universe that obeys the standard rules of inflation is less than 2%. It is a 5 sigma level anomaly, the gold standard for a real discovery in physics, and it simply will not go away. So, what could possibly create such a monumental cold patch in the baby universe? Cosmologists have proposed 3 leading explanations, each more mind-bending than the last. The first and most straightforward idea is that it's not a feature of the primordial universe at all, but an effect caused by a giant cosmic void lying between us and the CMB. This is known as the integrated Sachs-Wolfe effect. As light from the cosmic microwave background travels across the universe toward us, it must climb in and out of the gravitational wells of matter. If a photon enters a region that is still collapsing under gravity, it gains energy climbing out, making that part of the CMB appear slightly warmer. However, in a universe dominated by dark energy, the expansion is accelerating, which means that some large, fixed structures can actually stop collapsing and start being stretched apart. If a photon passes through one of these vast, underdense regions, a supervoid as it is being stretched by dark energy, it will actually lose energy climbing out of the weakening gravitational well. This loss of energy manifests as a cooling of the CMB in that direction. The cold spot in this view would be a shadow cast by the largest void we have ever seen, an emptiness so vast it literally saps the energy from the ancient light passing through it. The hunt for this proposed Eridanus supervoid has been intense. Astronomers have indeed found evidence of a large underdensity in that part of the sky, but there's a major problem. It doesn't seem nearly large enough or empty enough to account for the profound coldness of the spot. The void we have found might contribute to the effect, but it appears to be only a partial explanation, leaving a significant portion of the anomaly unexplained. When a simple, albeit colossal, void fails to fully solve the puzzle, physicists are forced to consider more exotic possibilities. The second explanation is truly a product of high-energy physics, a cosmic texture defect. To understand this, imagine the fabric of space-time in the very early universe undergoing a phase transition, much like water freezing into ice. As the universe cooled from an unimaginably hot, dense state, the fundamental fields that permeate all of reality may have settled into their current configurations. In most places, this settling happened smoothly, but in rare locations the fields could have gotten tangled, knotted up in a stable configuration that never quite smoothed out. These knots are known as cosmic textures. If such a texture existed, it would represent a localized concentration of energy that subtly warps space-time around it. As the primordial plasma of the early universe interacted with this knotted region of space, it would have created a specific signature, a large, circular cold spot in the cosmic microwave background, exactly like the one we observe. The texture itself would have long since unraveled and evaporated, but its gravitational imprint would remain frozen in the light, a fossil of a topological defect from the first moments of time. It's a beautiful and theoretically sound idea, but direct evidence for textures remains elusive, making this a compelling but unproven hypothesis. This leads us to the third and most profoundly radical explanation for the cold spot. that it is a bruise left from a collision with another universe. This idea emerges from the theory of eternal inflation and the multiverse. In this grand vision of reality, our universe is just one expanding bubble in a vast, frothing metacosmos, an infinite multiverse where new universes are constantly bubbling into existence. If two such bubble universes were to form close to each other in the greater multiverse, they could potentially collide as they both expand. The energy released at the boundary of such a cosmic collision would be immense. The cold spot in this breathtaking scenario would be the imprint of such an encounter. The collision would have occurred before the CMB was emitted, and the gravitational energy of the impact would have slightly altered the density and temperature of the plasma in that region, leaving behind a vast circular cold patch as a permanent scar. If this explanation were true, the cold spot would be the first empirical evidence for the existence of other universes, a tangible sign that our cosmos is not alone. It would be a discovery on par with realizing the Earth revolves around the Sun, fundamentally redefining our place in a reality of unimaginable scope. Ultimately, the cold spot remains one of cosmology's most persistent and challenging enigmas. It is a feature that standard inflationary cosmology struggles to account for, a data point that refuses to be smoothed away. Whether it is a shadow from a void, a fossil of a cosmic knot, or the scar of a multiverse collision, its very existence forces us to question the completeness of our story of the cosmos. It stands as a monumental reminder that even our most successful models are approximations, and that the universe, in its infinite creativity, always reserves the right to present us with something utterly unexpected, a mystery written in the cold, ancient light that challenges us to look deeper and dream bigger. And now we arrive at an anomaly that doesn't dwell in the distant cosmos or in the heart of a galaxy, but in the very foundation of reality, a phenomenon so bizarre that it seems to unravel the fabric of space and time as we know it. This is the enigma of quantum entanglement, a spooky action at a distance that Albert Einstein himself famously rejected, yet one that has been confirmed by experiment after experiment, forcing us to confront the possibility that our universe is fundamentally non-local, connected in ways that defy our classical intuition. At its core, quantum entanglement is a connection between two or more particles that persists no matter how far apart they are separated. Imagine you create a pair of electrons in a single quantum state. Their properties, like their spin, are linked. Before you measure them, they exist in a blurry superposition of all possible states. But the moment you measure the spin of one electron and find it, say, up, the other electron, even if it's now on the other side of the galaxy, will instantly be found to have a spin of down. This correlation is instantaneous. It appears that information has traveled between them faster than the speed of light, a direct violation of the local realism that Einstein held so dear. Local realism is the comforting idea that objects have definite properties even when we're not looking at them, and that no physical influence can travel faster than light. Entanglement shatters both of these assumptions, presenting a universe that is either not local, not real, or perhaps neither. For decades, this was a philosophical debate, a battle of interpretations between giants like Einstein and Niels Bohr. Einstein argued that quantum mechanics must be incomplete, that there must be hidden variables predetermined at the moment of entanglement that we simply couldn't see. He believed the particles were like a pair of gloves. If you find a left-handed glove in your pocket, you know instantly the one back home is right-handed, not because of spooky action, but because the handedness was set from the beginning. This was the core of the EPR paradox, a thought experiment designed to expose what Einstein saw as a flaw in quantum theory. It took until the 1960s for physicist John Bell to find a way to test this idea. Bell devised a mathematical theorem that showed if local hidden variables were real, then the correlations between entangled particles would have to obey a certain limit. If experiments showed correlations stronger than that limit, then local realism was false and the universe was genuinely as strange as quantum mechanics suggested. The experiments began, most famously those by Alain Aspect and his team in the 1980s. They created pairs of entangled photons and measured their properties in different directions. The results were definitive and earth-shattering. The correlations between the particles violated Bell's inequality. There were no hidden variables. The particles did not have predetermined states. Their connection was real, instantaneous, and non-local. Later experiments closed every conceivable loophole, separating the particles by hundreds of kilometers and ensuring the measurement settings were chosen randomly after the particles were already in flight, making any form of communication between them impossible. The verdict is in: the universe is not locally real. The act of measurement here truly does seem to affect the state of a particle over there in a way that transcends the space between them. This profound result has spawned a spectrum of interpretations, each attempting to make sense of a reality that seems to operate on magic. The most popular is the Copenhagen interpretation, which essentially says, "Don't ask." It posits that the wave function, which describes all possible states of a particle, collapses upon measurement into a single outcome, but it offers no mechanism for how this happens or why it should be instantaneous across vast distances. Then there is the many worlds interpretation, a truly cosmic solution. It suggests that the wave function never collapses. Instead, at the moment of measurement, reality splits into multiple branches. In one universe, you measured spin up and your partner measured spin down. In another parallel universe, you measured spin down and your partner up. There is no spooky action because every possible outcome actually happens. The correlation is built into the branching structure of reality itself. On the other end of the spectrum is the de Broglie-Bohm or pilot wave theory, which restores determinism by saying particles are guided by a pilot wave that pervades all of space. The particles have definite positions, but the wave connecting them is non-local, instantly updating across the entire universe to guide the particles' paths. It saves realism, but at the cost of accepting a blatant, inherent non-locality woven into the fabric of the cosmos. But the most profound implication of all this is that quantum entanglement might be forcing us to rewrite our understanding of space and time themselves. In our everyday world, space is the stage and time is the director, and events unfold upon it, but entanglement suggests that this stage might be an illusion. The deep connections between entangled particles seem to operate outside of space-time. They don't traverse the space between them, they simply ignore it. This has led to a radical idea championed by physicists like Juan Maldacena and Leonard Susskind, known as ER equals EPR. It's a proposal that links two seemingly unrelated concepts, Einstein-Rosen bridges, which are wormholes, and EPR entanglement. The mind-bending suggestion is that when two particles are entangled, they are not actually far apart in the classical sense. They are connected by a microscopic wormhole, a shortcut through the geometry of spacetime. Entanglement is the fabric of spacetime. In this view, the universe's vast classical geometry emerges from a vast underlying network of quantum entanglement. The three-dimensional space we live in and the time we experience could be a holographic projection of a two-dimensional information field where entanglement is the fundamental ingredient. This brings us to the heart of the quantum measurement problem, the question of why we experience a single, definite reality from a sea of quantum possibilities. The process of decoherence explains how a quantum system interacts with its environment and loses its quantum properties, but it doesn't solve the core mystery of the collapse. Resolving this may require the final, most dramatic step, rethinking the nature of spacetime. Perhaps the collapse of the wave function isn't a physical process in spacetime, but a process of spacetime. Some theories suggest that gravity, the force that shapes the cosmos on large scales, may play a key role in collapsing quantum superpositions. Roger Penrose, for instance, proposes that when a quantum system becomes too massive, its own gravitational self-energy causes it to collapse into a definite state. In this scenario, space-time itself becomes unstable to quantum superpositions and forces a definite reality to crystallize. The strange, non-local quantum realm and the familiar local space-time realm would then be two sides of the same coin, with the transition between them, the act of measurement being a fundamental property of how the universe stitches together reality from its quantum components. Quantum entanglement, therefore, is not just a curious oddity of tiny particles. It is a direct window into the operating system of the cosmos, hinting that space and time are not the fundamental stage, but a secondary, emergent consequence of a far deeper, more connected, and utterly non-local quantum reality. We now venture into a cosmic accounting era of staggering proportions, one that involves the very stuff you, me, and all the stars are made of. This is the baffling case of the universe's missing baryons. When we talk about the mysterious dark matter and dark energy that dominate the cosmos, it's easy to forget that ordinary matter, the protons, neutrons, and electrons that form planets, people, and every star we see is itself a rare and precious commodity, making up less than 5% of the universe's total energy budget. Yet cosmologists have been faced with a deeply unsettling realization. We can't even find all of that measly 5%. According to our gold standard model of Big Bang nucleosynthesis, which perfectly predicts the primordial abundances of light elements like hydrogen and helium, we know precisely how much of this ordinary, or baryonic, matter should have been created in the first few minutes of the universe. It's a specific number, a fundamental density that is woven into the fabric of our cosmic models. But when astronomers add up everything they can see, all the stars, all the glowing gas in galaxies, all the dust, they come up hilariously short. We're talking about a deficit of roughly half of all the normal matter that should be out there. It's as if the universe did its inventory, counted all the trees, but somehow misplaced entire forests. The search for this missing matter has been a decades-long detective story. For a long time, scientists thought it might be hiding in plain sight, perhaps in faint, undetected dwarf galaxies or in cold, dark clouds of gas drifting in the emptiness between stars. But careful surveys have ruled out these possibilities. There simply isn't enough mass there to balance the books. The plot thickened when astronomers realized that the modern inventory of galaxies and clusters doesn't match the amount of matter we know was present in the early universe, as imprinted on the cosmic microwave background. This created a profound temporal paradox. The universe started with a certain amount of baryonic stuff, but today that stuff seems to have vanished into thin air. The only logical conclusion is that the missing matter isn't hiding in galaxies at all, but in a far more elusive and vast repository, the space between the galaxies themselves, in the cosmic web that structures the universe. This is where our story takes a dramatic turn, pointing toward a hypothetical hiding place known as the warm-hot intergalactic medium, or WIM for short. Imagine the universe's large-scale structure not as a collection of isolated islands, but as a single, interconnected web. Galaxies and clusters are the dense knots in this web, connected by immense, thread-like filaments of dark matter. According to our simulations, these filaments should also be traced by ordinary matter, a diffuse, superheated gas. This isn't a cold, dark gas, but a plasma so hot between 100,000 and 10 million degrees Kelvin that it doesn't emit visible light. Instead, it glows faintly in high-energy X-rays, making it incredibly difficult to detect with conventional telescopes. Furthermore, this gas is so thin, with a density of perhaps just 1 atom per cubic meter, that it's virtually transparent. You could look right through a filament of the WIM that's millions of light years long and see nothing at all. This is the leading theoretical candidate for the universe's lost matter, a ghostly, seething ocean of gas filling the intergalactic voids, the true backbone of the cosmic web. Proving the existence of the WIM, however, has required extraordinary ingenuity. Since we can't see this gas directly, astronomers use a clever trick of nature, absorption line studies. The method works by using the universe's natural flashlights distant, brilliant objects known as quasars. As the intense light from a quasar travels across billions of light years to reach our telescopes, it passes through these invisible filaments of the WIM. The highly ionized atoms in the hot gas oxygen, nitrogen, carbon act like a cosmic filter, absorbing very specific wavelengths of the quasar's light. When we break that light down into a spectrum, we see telltale, dark lines where the energy has been snatched away. It's forensic science on a cosmic scale, where the crime scene is the void of space, and the evidence is a pattern of missing colors in the light of a distant beacon. For years, the evidence was frustratingly sparse, just a handful of tentative detections, but recently the tide has turned. By combining data from multiple observatories, including the XMM Newton and Chandra X-ray telescopes, and cross-referencing with immense galaxy surveys to map the predicted locations of the cosmic web, astronomers have begun to find the signal. They've detected the absorption signatures of highly ionized oxygen in the lines of sight to quasars, precisely aligned with the predicted positions of the WIM filaments. It's like finally getting a fingerprint from a ghost we've been chasing for 50 years. The hunt is far from over, though. Each detection is painstaking work, and we are still only seeing the very densest and hottest parts of this elusive medium. The challenge now is to map its full extent, to measure its temperature and density distribution, and to finally close the cosmic budget, confirming that this warm, hot intergalactic plasma truly does account for every last missing baryon. New instruments like the recently launched XRISM satellite and future proposed missions are designed with the explicit goal of performing a detailed census of this intergalactic material. They will have the spectral resolution to see the faint fingerprints of other elements and to probe cooler, even more diffuse gas that current telescopes simply can't perceive. Solving the mystery of the missing baryons is about more than just balancing an equation. It's about completing our picture of the cosmic ecosystem. It reveals that the space between galaxies is not a true void, but a dynamic, structured environment containing the majority of the normal matter in the universe. This missing matter is the hidden reservoir from which galaxies form and grow, the connective tissue of the cosmos, and its discovery is a triumphant testament to the power of indirect observation and theoretical prediction in our quest to understand the architecture of everything. The discovery that the universe is not just expanding, but that its expansion is accelerating, stands as one of the most profound and unsettling revelations in the history of science. For much of the 20th century, the prevailing cosmological question was whether the gravitational pull of all the matter in the cosmos would be enough to eventually halt the Big Bang's initial outward rush, leading to a big crunch. The expectation was that the universe's expansion should be slowing down, coasting like a car gradually losing speed on a long, flat highway. But in the late 1990s, two independent teams of astronomers, racing to measure the deceleration rate by observing distant stellar explosions, found the exact opposite. Their data revealed a universe that is not slowing down at all, but speeding up, as if the driver had suddenly stomped on the accelerator. This was the breathtaking anomaly of the runaway universe, a finding so shocking it would later earn the Nobel Prize and force a complete rewrite of our cosmic playbook. The key to this discovery was a specific kind of cosmic mile marker, type I supernova. These stellar explosions are not just random cataclysms, they are nature's most reliable standard candles. They occur in binary star systems where a dense white dwarf siphons material from a companion star. Once the white dwarf reaches a critical mass limit about 1.4 times the mass of our Sun, a runaway thermonuclear explosion tears it apart. Because this detonation always happens at the same mass threshold, the intrinsic brightness of these supernovae is remarkably consistent. By measuring how bright they appear from Earth, astronomers can calculate their precise distance. Furthermore, by analyzing the redshift of their light, how much it has been stretched by the expansion of the universe, we can determine how fast they were moving away from us when they exploded. By looking at extremely distant and therefore ancient supernova, these teams were effectively looking back in time, comparing the expansion rate billions of years ago to the rate today. The results, announced almost simultaneously by the teams led by Saul Perlmutter and by Brian Schmidt and Adam Rees, were unequivocal and earth-shattering. The distant, ancient supernova were fainter than they should have been if the universe had been expanding at its current rate all along. The only logical explanation was that these stellar explosions were farther away than expected. This meant that in the past, the universe was expanding more slowly than it is now. The expansion has been accelerating over billions of years. Imagine throwing a ball into the air, and instead of it slowing down and falling back, it shot upward faster and faster, defying gravity. That is the cosmic equivalent of what the data showed. The universe, against all expectations, is flying apart at an ever-increasing rate. This observation could not be explained by any known form of matter or energy. Gravity, as we understand it, is exclusively attractive. It pulls things together, it cannot push them apart. To drive cosmic acceleration, there must be a pervasive, repulsive force acting on the very fabric of space-time itself. This mysterious something was dubbed dark energy, and it is now calculated to constitute about 68% of the entire energy density of the universe. It is the dominant component of reality, with dark matter making up about 27%, and all the ordinary matter, every star, planet, and person comprising a mere 5%. Dark energy is the engine of the cosmos, yet we have almost no idea what it actually is. The most straightforward, and in some ways the most elegant, explanation for dark energy is Einstein's cosmological constant. Ironically, Einstein originally introduced this concept, represented by the Greek letter lambda, into his equations of general relativity to achieve a static universe, which was the prevailing belief at the time. When the universe was later found to be expanding, he famously called it his greatest blunder and discarded the idea. But with the discovery of acceleration, the cosmological constant was resurrected. In this context, it represents a constant energy density inherent to the vacuum of space itself. As the universe expands and more space comes into existence, more of this vacuum energy is created, maintaining a constant density that drives the acceleration ever forward. It's a simple, one-number solution that fits the observational data remarkably well. However, this elegant solution introduces what is arguably the most severe theoretical problem in all of physics, the cosmological constant problem. When physicists attempt to calculate the expected energy density of the vacuum using quantum field theory, they sum up the contributions from all the fleeting quantum fluctuations and virtual particles that pop in and out of existence. The result they get is a number that is, quite literally, off the charts. The theoretical prediction exceeds the observed value of the cosmological constant by a factor of 10 to the power of 120. That's a 1 followed by 120 zeros. This is not just a small error, it is the worst discrepancy between theory and observation in the entire history of science. It's like using the world's most advanced physics to predict the weight of a single electron and getting an answer heavier than the entire observable universe. This colossal failure tells us that something is profoundly wrong with our understanding, either of the quantum vacuum, of gravity, or of both. This enormous problem has led physicists to explore radical alternatives to a simple, constant dark energy. One compelling idea is that dark energy is not a constant at all, but a dynamic field that evolves over time, much like the hypothetical, inflaton field that drove the ultra-fast expansion of the universe during the Big Bang. This concept is often referred to as quintessence. In this model, the energy density of this field can slowly change, perhaps weakening or strengthening over cosmic history. This would mean the acceleration of the universe is not a permanent, fixed feature. Perhaps we are living in a special era where this quintessence field is driving acceleration, but in the distant past or far future, its behavior could be completely different. Some quintessence models even allow for the possibility that the repulsive force could someday reverse, turning into an attractive force that could ultimately halt the expansion and pull the universe back together in a big rip or a big crunch. The search for evidence of evolving dark energy is a primary goal for next-generation telescopes, which will look for tiny deviations in the acceleration rate over different cosmic epochs. Another, even more profound, line of thought questions whether dark energy is even a form of energy at all. Perhaps it is an illusion, a signal that our theory of gravity itself is flawed on the largest imaginable scales. Einstein's general relativity has passed every test thrown at it, from the orbit of Mercury to the bending of light around the Sun. But it has never been rigorously tested across the vast, homogeneous distances of intergalactic space. What if general relativity needs to be modified? Theories of modified gravity, such as massive gravity or tensor vector scalar gravity, attempt to tweak Einstein's equations so that on the scale of galaxies they behave just as we observe, but on cosmic scales they naturally produce an accelerated expansion without the need for any exotic dark energy component. The challenge for these theories is to consistently explain all cosmological phenomena from the cosmic microwave background to the large-scale structure of galaxies without reintroducing the need for some form of dark energy, a hurdle that has proven incredibly difficult to clear. The implications of the runaway universe are as existential as they are scientific. If dark energy is indeed a cosmological constant, then the acceleration will continue indefinitely. In a future trillions of years from now, the expansion will have become so rapid that all galaxies outside our local group will have been pushed beyond our cosmic horizon, their light forever too redshifted and faint to ever reach us again. The universe for any future civilization will be a lonely, isolated island of stars in an infinite, ever-darkening void. The discovery of this acceleration has fundamentally reshaped our cosmic destiny, replacing a potentially cyclical universe with one that is headed toward a cold, lonely, and final dissolution. The runaway universe is the ultimate anomaly. A discovery that revealed the dominant force shaping our reality is a mysterious, repulsive presence whose true nature remains one of the greatest and most humbling mysteries in all of modern physics. But if the runaway universe describes a cosmic-scale fate, our next anomaly plunges us into the ultimate abyss, confronting a paradox that strikes at the very meaning of reality. This is the black hole information paradox, a puzzle so profound that it set Stephen Hawking against the entire framework of quantum mechanics, and its potential resolution might require us to rewrite the laws of physics. At its heart, this paradox asks a deceptively simple question. When something falls into a black hole, what happens to the information that described it? According to our best understanding, the answer should be nothing. Information must be preserved. But according to Hawking's own work, it appears to be utterly erased, a cosmic deletion that threatens to unravel our grasp of the universe. To understand the stakes, you first have to grasp a cornerstone of quantum mechanics, the principle of unitarity. This is the idea that information is never truly lost. If you could somehow track every single particle and every quantum state in a system, you could, in principle, reverse time and see exactly what the system looked like in the past. It's the ultimate cosmic DVR. If you burn a book, the information isn't really gone. It's just transformed into the specific arrangement of ash, smoke, and heat. A hypothetical superintelligence could, from that smoke and ash, reconstruct the exact text of the book. This reversibility is fundamental. It means the universe is predictable in its past and future states. Now enter the black hole. In the 1970s, Stephen Hawking made a stunning discovery. By applying quantum field theory to the curved space-time around a black hole, he realized that black holes aren't completely black. They slowly leak radiation, now known as Hawking radiation. This radiation is generated when pairs of virtual particles pop into existence near the event horizon, the point of no return. Normally, these particle-antiparticle pairs annihilate each other almost instantly. But if one particle falls into the black hole while its partner escapes, the escaping particle becomes real, carrying away a tiny bit of the black hole's energy. Over eons, this process causes the black hole to slowly evaporate, shrinking until it presumably vanishes entirely. And here lies the paradox. Hawking's original calculations showed that this escaping radiation is completely random and thermal. It's pure heat, a featureless fuzz that carries no information about what fell into the black hole. It doesn't matter if you threw in a piano, a library of encyclopedias, or a collection of old tires. The Hawking radiation that comes out would be exactly the same. So when the black hole finally evaporates and disappears, what happened to the information that described the piano, the books, or the tires? According to Hawking's result, it has been permanently erased from the universe. This violates unitarity. It's the equivalent of burning that book, but then having the very laws of physics prevent anyone, even a super-intelligence, from ever reconstructing it from the ashes. Hawking famously bet other physicists that information was indeed lost, a bet he later conceded, but the deep problem he identified remains a central puzzle in theoretical physics. The scientific community has rallied to find a way to save information, leading to some of the most mind-bending concepts in modern physics. One of the most influential proposals is the holographic principle. This radical idea suggests that all the information that falls into a black hole is not stored in its mysterious interior, but is somehow encoded on its two-dimensional surface, the event horizon. Think of it like a cosmic DVD. A DVD is a flat, two-dimensional disc, but it contains all the information needed to reconstruct a three-dimensional movie. Similarly, the holographic principle posits that the event horizon acts as a vast, pixelated screen, with each tiny blank area storing a single bit of quantum information. As objects fall in, their information is scrambled and imprinted onto this vibrating, two-dimensional membrane. Then, when Hawking radiation is emitted, it's not random. It's actually encoded with this very information, slowly leaking the data back out into the universe as the black hole evaporates. The information was never really inside the black hole. It was always on the surface, being gradually transmitted out via the radiation. This preserves unitarity, but at the cost of redefining our notion of reality, suggesting that our three-dimensional world might be a projection from a two-dimensional boundary at the edge of the universe. Another dramatic and highly controversial solution is the black hole firewall proposal. If information is to be saved, then the principle of locality, the idea that different points in space are distinct, might have to be sacrificed at the event horizon. The firewall hypothesis suggests that the event horizon is not the smooth, uneventful gateway described by general relativity. Instead, it is a blistering wall of high-energy particles and literal firewall that would instantly incinerate anything crossing it. This solves the information paradox by severing the connection between the inside and outside of the black hole in a violent, information-scrambling event. While this preserves the purity of quantum mechanics, it creates a new problem. It violates Einstein's equivalence principle, which states that an observer falling into a black hole should not notice anything special as they cross the event horizon. You can't have a smooth space-time and a raging firewall at the same point. So, physicists are forced to choose, sacrifice the smoothness of space-time, a cornerstone of general relativity, or sacrifice the preservation of information, a cornerstone of quantum mechanics. The firewall remains a hotly debated, almost desperate solution that highlights the deep tension between our two most successful theories. Recent decades have seen tremendous progress, largely driven by new mathematical tools and insights from string theory. One of the most promising developments involves precisely calculating the entropy of black holes. Entropy is a measure of disorder, but in information theory, it corresponds to the amount of hidden information a system contains. Hawking himself discovered that a black hole's entropy is proportional to the area of its event horizon, not its volume. This was the first major hint of the holographic principle. Modern research has pushed this much further, using concepts like the AD/CFT correspondence, a specific realization of the holographic principle, to show how the information of objects falling into a certain type of black hole can be perfectly mirrored in the behavior of a quantum field theory on its boundary. Furthermore, refined calculations of Hawking radiation now suggest it is not perfectly thermal after all. The radiation particles are subtly entangled with each other and with the black hole's interior in an intricate web of quantum connections. As the black hole evaporates, these correlations can, in theory, carry the information outward, preserving it. The challenge is doing this without creating a firewall or some other violent violation of general relativity. The current frontier involves understanding the geometry of islands in the gravitational path integral regions inside the black hole that somehow become part of the external quantum system responsible for radiating the information back out. It's complex, cutting-edge work that is slowly building a bridge across the paradox. Ultimately, resolving the black hole information paradox is not just an academic exercise. It is a crucial battleground in the century-long quest to unify general relativity with quantum mechanics. A theory of quantum gravity must be able to tell us what happens to information at the edge of a black hole. The fate of a single bit of data falling into this ultimate prison is a proxy for the fate of causality, locality, and the very logical structure of our universe. The paradox forces us to confront the fact that our classical picture of space and time, with its smooth, deterministic fabric, is fundamentally incompatible with the fuzzy, probabilistic, and interconnected world of the quantum. A successful resolution will likely show us that one of these pictures is an illusion, an emergent approximation of a far stranger and more wonderful underlying reality. The black hole, therefore, is not just a cosmic vacuum cleaner. It is the universe's most demanding teacher, using its immense gravitational grip to crush our comfortable assumptions and force us to invent a new language to describe the world. If the black hole information paradox reveals a conflict between our theories of the very large and the very small, then our next anomaly exposes a rift in the very foundations of physics, so vast it has been called the worst prediction in the history of science. We've discussed dark energy, the mysterious force accelerating the universe, and the cosmological constant as its simplest explanation. But this elegant solution comes with an almost incomprehensible price tag known as the vacuum catastrophe. The problem is this: when we use our most successful theory of the small quantum field theory to calculate how much energy should be writhing in the empty space of a vacuum, we get a number. And when we use our observations of the cosmos to measure how much energy is actually there, driving the acceleration of the universe, we get another number. These two numbers are not just a little different, they are separated by a factor of 10 to the power of 120. That is a 1 followed by 120 zeros. To put that staggering discrepancy into perspective, the difference between the theoretical prediction and the observed value is greater than the difference in scale between a single proton and the entire observable universe. It is a failure of such monumental proportions that it cannot be ignored. It demands that our fundamental understanding of reality is missing something profound. To grasp why this calculation is so important and so baffling, we need to understand what physicists mean by the vacuum. In our everyday experience, a vacuum is just empty space, a true void. But quantum mechanics tells us that there is no such thing as true emptiness. At the tiniest scales, space is a seething, bubbling foam. Pairs of virtual particles and their antiparticles constantly pop into existence, borrowing energy from the vacuum for an incredibly brief moment before annihilating each other and returning the energy. This isn't just a theoretical curiosity. We see the effects of these quantum fluctuations in measurable phenomena, like the subtle shift in the energy levels of atoms, known as the Lamb shift, or the Casimir effect, where two metal plates placed very close together in a vacuum are gently pushed together by the pressure of these virtual particles popping off outside them. So, the vacuum has energy, and according to quantum field theory, we should be able to add up the contributions from every possible quantum field, the electromagnetic field, the electron field, the quark fields, and so on, to get the total energy density of empty space. This is where the calculation goes off the rails. When physicists perform this sum, the result is an energy density of around 10 to the power of 112 ergs per cubic centimeter. It's an astronomically large number, suggesting that every tiny cubic centimeter of space should contain unimaginable power. Now, let's look at the other side of the equation, the observed value. We don't measure the vacuum energy directly. Instead, we infer it from its effect on the cosmos, the acceleration of the universe's expansion. By observing distant supernovae and the large-scale structure of the universe, cosmologists can determine how much repulsive energy is needed to drive the acceleration we see. This gives us the value for the cosmological constant, and that value is about 10 to the power of -8 ergs per cubic centimeter. It is an incredibly small, delicate amount of energy, but it's enough to dominate the universe and dictate its ultimate fate. So we have a prediction of 10 to the power of 112 and an observation of 10 to the power of -8. The difference is a factor of 10 to the 120th power. The vacuum, according to our best theories of the small, should be so densely packed with energy that it would have ripped the universe apart in a catastrophic expansion within the first fraction of a second of the Big Bang. The fact that we exist in a stable, slowly accelerating universe means that something is terribly wrong with our calculation. The theoretical value is wrong by 120 orders of magnitude. Faced with such an immense problem, physicists have been forced to consider solutions that range from the highly technical to the deeply philosophical. One of the most pursued avenues is the idea of supersymmetry. This elegant theory proposes that every known particle has a hidden super-partner particle. For the electron, there would be a selectron, for the quark, a squark. The beauty of supersymmetry is that the contributions of these superpartners to the vacuum energy would have the opposite sign to their normal matter counterparts. In a perfectly supersymmetric universe, these contributions would cancel each other out exactly, bringing the net vacuum energy to zero. This would be a perfect and beautiful solution. However, we live in a very non-supersymmetric world. If these superpartners exist, they must be much heavier than their normal counterparts. Otherwise, we would have detected them in particle colliders like the Large Hadron Collider. This broken supersymmetry means the cancellation is no longer perfect, but it could, in principle, reduce the discrepancy from 120 orders of magnitude down to a more manageable 50 or 60. That's still a colossal error, but it shows how new physics could potentially tame the calculation. The ongoing failure to find any direct evidence for supersymmetry, however, has left this solution in a state of uncertainty. This leads to another, more controversial line of reasoning, the anthropic principle. In this view, the cosmological constant isn't determined by a fundamental law of physics, but is instead a random variable that can take on different values in different parts of a vast multiverse. In an unimaginably large ensemble of universes, most would have a vacuum energy so large that galaxies, stars, and planets could never form, or so negative that the universe would immediately collapse. We quite obviously find ourselves in one of the rare universes where the vacuum energy is minuscule, just right for allowing the formation of complex structures and ultimately life forms capable of observing it. The value isn't explained by a fundamental equation, it's explained by our own existence as observers. For many physicists, this is a deeply unsatisfying cop-out, a retreat from the goal of fundamental explanation. For others, it is a sober acknowledgement that some constants in nature may be environmental rather than derived from first principles, and that our universe's habitability is a crucial piece of data that any successful theory must account for. Beyond these major ideas, other possibilities linger in the background. Perhaps there is some unknown dynamic cancellation mechanism that we haven't yet discovered, a symmetry or a principle that forces the vacuum energy to be exactly zero, with the tiny value we observe being due to some other minor effect. Or perhaps our understanding of gravity is the issue. The calculation of the quantum vacuum energy and its gravitational effect relies on the assumption that gravity couples to this energy in a straightforward way, as described by general relativity. It's possible that on the largest cosmic scales, gravity behaves differently, effectively filtering out the immense quantum vacuum energy and only responding to the tiny leftover we call dark energy. This would mean that the vacuum catastrophe is not a problem with quantum field theory, but with our theory of gravity, a signal that general relativity needs modification in the infrared or low energy limit. The implications of the vacuum catastrophe extend to the very end of time. If the dark energy is indeed a constant cosmological constant, then the acceleration of the universe will continue forever. Billions of years from now, all galaxies outside our local group will have been pushed beyond our cosmic horizon, their light forever too redshifted to see. The universe will become a cold, dark, and empty place with isolated islands of stars slowly dying out. This is known as the heat death. However, if the vacuum energy is not constant, but is instead a dynamic field like quintessence, other fates are possible. It could decay away to nothing, allowing the universe to resume a more sedate expansion. Or it could strengthen, leading to a big rip, where the repulsive force becomes so powerful that it tears apart galaxies, solar systems, planets, and eventually the very atoms that constitute matter. The vacuum catastrophe is therefore not just an abstract theoretical problem. It is directly linked to the ultimate destiny of all existence. It stands as a monument to our ignorance, a 120 order of magnitude reminder that for all our progress, the deepest nature of reality, the energy of nothing itself remains one of the greatest unsolved mysteries in physics. And so we arrive at a puzzle so deeply embedded in the laws of physics that it questions the very stability of our reality. This is the hierarchy problem, and it asks a deceptively simple question: why is gravity so absurdly weak? Think about it for a moment. A tiny refrigerator magnet can generate enough electromagnetic force to defy the gravitational pull of the entire Earth, a planet weighing over 6 sextillion tons. This isn't just a small difference, it's a chasm of staggering proportions. The force of gravity is roughly 10 to the power of 36 times weaker than the electromagnetic force. That's a 1 followed by 36 zeros. It is the feeblest by far of the 4 fundamental forces, a faint whisper in a universe dominated by the nuclear and electromagnetic shouts. This incredible disparity isn't just a curiosity. It points to a profound fine-tuning issue that strikes at the heart of our most successful particle theory, the Standard Model. To truly grasp the depth of this problem, we need to look at the energy scales where the fundamental forces are thought to unify. At one extreme, we have the electroweak scale, the energy at which the electromagnetic and weak nuclear forces merge into a single electroweak force. This energy, around 246 giga-electron volts, is the realm of the Higgs boson and the highest energies we can currently probe with machines like the Large Hadron Collider. It's the energy of our observable, everyday particle physics. At the other extreme lies the Planck scale, the energy at which gravity is expected to become as strong as the other forces, and quantum gravitational effects dominate. This energy is a mind-numbing 10 to the power of 19 giga-electron volts. The difference between these two scales is a factor of 10 to the power of 17. To put that in perspective, it's the difference between the mass of a single proton and the mass of a small grain of sand, a difference of scale that seems to defy any natural explanation. Why do these two fundamental pillars of physics, the Higgs scale and the gravity scale, exist in such wildly different neighborhoods of the cosmic energy landscape? The problem becomes acute when we consider the Higgs boson itself. The Higgs field is what gives other fundamental particles their mass, but its own mass is incredibly sensitive to quantum corrections. In the quantum world, the Higgs mass is constantly being jostled by its interactions with virtual particles that flicker in and out of existence. Every known particle and every possible unknown particle contributes to this quantum jitter. Theoretically, these contributions should drive the Higgs mass, and therefore the electroweak scale, all the way up to the enormous Planck scale. It's as if you were trying to weigh a feather, but every subatomic particle in the universe kept jumping onto the scale, making it read the weight of a mountain. For the Higgs mass to remain at its relatively low, observed value, there must be an unbelievable, perfect cancellation between these enormous quantum corrections. The positive contributions must cancel out the negative ones to 1 part in 10 to the power of 34. This is a degree of fine-tuning so exquisite that it seems to demand an explanation beyond sheer, mind-boggling coincidence. It's the universe's most precise balancing act, and physicists are deeply uncomfortable with the idea that it's just a cosmic accident. This profound discomfort has driven the search for physical mechanisms that could naturally explain this stability, and one of the most celebrated candidates has been supersymmetry. This beautiful theory proposes a profound symmetry between the two fundamental classes of particles: fermions, which are the building blocks of matter like quarks and electrons, and bosons, which are the force carriers like photons and gluons. Supersymmetry posits that for every known fermion, there is a bosonic superpartner, and for every known boson, a fermionic superpartner. The magic of this partnership is that the quantum contributions of a particle and its superpartner to the Higgs mass are equal in magnitude but opposite in sign. They cancel each other out perfectly. In a perfectly unbroken supersymmetric universe, the delicate Higgs mass would be protected from these wild quantum fluctuations. The feather would remain a feather, its weight stabilized by an invisible, mirrored counterpart. This would naturally explain why the electroweak scale is so much lower than the Planck scale. The catch, of course, is that we don't see these superpartners in our everyday world. If they exist, supersymmetry must be a broken symmetry, meaning the superpartners are much heavier than their standard counterparts. The hope was that the Large Hadron Collider would discover these particles, providing a direct solution to the hierarchy problem. While the LHC brilliantly discovered the Higgs boson, it has so far found no evidence for supersymmetry, pushing the possible mass of these hypothetical particles to ever higher energies and causing many physicists to reassess this once bulletproof idea. Another, even more mind-bending solution involves rethinking the very dimensionality of our universe. What if gravity only appears weak because it is not confined to our three-dimensional space like the other forces? This is the core idea behind theories with large extra dimensions, most notably the Randall-Sundrum model. Imagine our universe as a four-dimensional membrane or brain floating within a higher dimensional bulk. The strong, weak, and electromagnetic forces are stuck to our brain like ink on a sheet of paper. Gravity, however, is different. It can leak out, spreading its lines of force into these extra, compactified dimensions. From our perspective, trapped on our three-dimensional brain, the gravitational force seems diluted, spread thin across a reality we cannot perceive. The Planck scale in this view isn't fundamentally different. It's an illusion created by geometry. The true energy scale of gravity could be much lower, perhaps even as low as the electroweak scale itself. This would mean that the hierarchy problem is not a problem of fine-tuning, but of perspective. The thrilling implication is that we could potentially create microscopic black holes or detect signatures of these extra dimensions at particle colliders, as gravity would become strong at energies we can actually reach. While evidence for this remains elusive, it demonstrates the kind of radical reimagining of spacetime that the hierarchy problem forces upon us. A third compelling line of thought suggests that the Higgs boson might not be a fundamental particle at all. Just as the proton is a composite particle made of more fundamental quarks, the Higgs could be a bound state of new, more basic constituents. This idea, known as Higgs compositeness or technicolor, posits a new, powerful, strong force that acts at a much higher energy. At the low energies we probe, this force binds its constituent particles together to form what we see as the Higgs boson. In such models, the Higgs mass is naturally stabilized by the compositeness scale, much like the mass of the proton is protected from quantum corrections by the strong nuclear force that binds it. The hierarchy problem is solved because the Higgs isn't an elementary particle vulnerable to wild quantum swings, but a composite object with a natural size and mass. The challenge for these models has been to produce a Higgs boson that looks and behaves exactly like the one discovered at the LHC, which appears to be remarkably elementary and standard in its properties. The relentless drive to solve the hierarchy problem is not merely an academic exercise. It is the engine behind much of modern experimental particle physics and cosmology. The Large Hadron Collider was built not just to find the Higgs, but to probe the very territory where solutions to the hierarchy problem should manifest, whether in the form of supersymmetric particles, signs of extra dimensions, or resonances hinting at Higgs compositeness. Its continued operation and the planning for even more powerful future colliders is a direct response to this fundamental mystery, but the search doesn't end in Geneva. The extreme fine-tuning of the Higgs mass also has profound implications for the early universe and the nature of dark matter. Some models that stabilize the hierarchy, like certain supersymmetric theories, naturally provide a candidate for dark matter in the form of the lightest supersymmetric particle, a stable, weakly interacting massive particle that could pervade the cosmos. Furthermore, the behavior of the Higgs field in the early universe is intimately tied to cosmic inflation and the ultimate fate of the cosmos. A metastable Higgs vacuum could imply that our universe is not in its true lowest energy state and could potentially decay into a bubble of nothingness in a catastrophic phase transition, a cosmological outcome directly linked to the precise values we are trying to explain. Ultimately, the hierarchy problem is more than just a numerical discrepancy. It is a profound philosophical guide. It tells us with near certainty that the standard model of particle physics, for all its spectacular success, is incomplete. It is a low-energy effective theory, a glimpse of a deeper, more symmetric and more complex reality that operates at energies we have yet to access. The incredible weakness of gravity is a constant, nagging clue, a signpost pointing toward new physics that must exist to protect the fabric of our reality from quantum chaos. Whether the answer lies in supersymmetry, hidden dimensions, compositeness, or something even more extraordinary that we haven't yet conceived, the hierarchy problem ensures that our quest to understand the fundamental forces of nature remains one of the most exciting and urgent adventures in all of science. Now, as we approach the end of our journey, we confront an anomaly that is arguably the most personal of all, a mystery that strikes at the very existence of everything we know and love. Why is there something rather than nothing? This is not just a philosophical question. It is a concrete, quantitative puzzle in physics known as the matter-antimatter asymmetry. According to our most fundamental theories, the Big Bang should have created equal amounts of matter and antimatter. And since matter and antimatter are perfect mirror images, they should have completely annihilated each other upon contact, leaving behind a universe filled with nothing but a sea of featureless light. There should be no stars, no planets, no people. The fact that you are here to watch this video, that the screen you're looking at exists at all, is proof that this perfect symmetry was broken. Somehow, for every billion pairs of matter and antimatter particles that annihilated in the early universe, a single solitary matter particle was left over. That 1 in a billion survivor is the seed for every galaxy, every star, and every atom in our bodies. We are the residue of a cosmic imperfection, and we have no definitive explanation for why this fortunate flaw exists. The theoretical framework for creating this imbalance is known as baryogenesis, and it requires 3 specific conditions, known as the Sakharov conditions, to be met. First, the universe must have processes that violate the conservation of baryon number. Baryons are particles like protons and neutrons, and this rule essentially says you can't create or destroy the net amount of matter in the universe. Clearly, this rule had to be broken at some point to create our matter-dominated reality. Second, there must be a violation of both charge C and charge parity CP symmetry. This gets to the heart of the mirror image problem. Charge symmetry means the laws of physics should be the same if you swap every particle with its antiparticle. Parity symmetry means the laws should be the same in a mirror universe where left and right are reversed. If both of these symmetries held perfectly, matter and antimatter would behave in lockstep, and any process that created one would create the other in equal measure, leading to total annihilation. To create an excess of matter, you need a process that treats matter and antimatter slightly differently, that favors one over the other in a fundamental way. The third condition is that all of this must occur out of thermal equilibrium. If the universe were in a perfect, smooth equilibrium, any budding asymmetry would simply be wiped away as quickly as it formed. You need a dramatic, out-of-balance event like a phase transition to freeze in the asymmetry before the universe can smooth it out. We know that one of these ingredients, CP violation, is real. It has been observed in the delicate world of particle physics. Experiments studying particles called neutral kaons and B mesons have shown that they and their antiparticles do not decay in exactly the same way. There is a tiny, measurable preference in the rates. This was a monumental discovery, proving that the universe does, at some level, have a handedness, a fundamental preference for matter over antimatter. However, there is a catastrophic problem. The amount of CP violation we have measured in the laboratory is far too small to account for the overwhelming matter dominance we see in the cosmos. It's like having a recipe that calls for a cup of salt to make a meal palatable, but we've only found a single grain. The standard model of particle physics, for all its glory, possesses a mechanism for CP violation that is utterly insufficient to generate the 1 in a billion surplus we require. This means the source of our existence must lie beyond the physics we currently understand and have verified. This glaring insufficiency has forced physicists to propose more speculative and dramatic solutions. One of the most compelling ideas is leptogenesis. This elegant theory shifts the primary action from the realm of baryons, protons, and neutrons to the realm of leptons, specifically the elusive and mysterious neutrinos. The theory posits the existence of incredibly heavy, right-handed neutrinos in the very early universe. As these behemoths decayed, they would have done so in a CP-violating way, producing slightly more ordinary matter particles than antimatter particles. This initial lepton asymmetry could then be converted into the baryon asymmetry we see today through a subtle quantum process called Sphaleron interactions, which can flip leptons into baryons. In this scenario, the ultimate reason we exist is tied to the properties of the heaviest neutrinos in the first moments of time, a beautiful and profound connection between the tiniest neutrinos and the largest cosmic structures. Another fascinating, though more speculative, proposal involves the evaporation of primordial black holes. Imagine the universe in its first frantic moments, a seething cauldron of energy where microscopic black holes could have spontaneously formed. As we discussed with Hawking radiation, black holes slowly evaporate, but according to some theories, this evaporation process might not be symmetrical. It's possible that these tiny black holes could have radiated away more matter than antimatter, or vice versa, acting as countless little factories for baryogenesis. If a vast population of these primordial black holes evaporated in the early universe, their collective output could have tipped the cosmic scales decisively in favor of matter, seeding the void with the raw material for future galaxies. This idea elegantly links the mystery of our existence to the quantum gravitational physics of black holes, another of our great cosmic puzzles. The implications of this asymmetry are as absolute as they get. It determines whether the universe is a vibrant, complex, and structured place, or a barren, empty void. Without this 1 in a billion break in symmetry, the cosmos would be a vast, expanding cloud of radiation, utterly dark and lifeless for all eternity. There would be no chemistry, no planets, no light from stars. The existence of any structure at all is a direct testament to this primordial imbalance. Every atom in your body is a relic of that ancient battle, a survivor of the great annihilation that defined the first second of existence. The matter-antimatter asymmetry is therefore the ultimate anomaly. It is not a curiosity about a distant quasar or a subtle glitch in a spacecraft's trajectory. It is the foundational question of why there is a universe here for us to study at all. Solving it would mean understanding the very first and most important fork in the road for our cosmos, the moment physics decided that something was better than nothing. And finally, we arrive at an anomaly so fundamental that it forced cosmologists to completely rewrite the opening chapter of cosmic history. This is the horizon problem, and it asks a deeply unsettling question about the uniformity of the universe. Look up at the night sky in any direction you choose. The cosmic microwave background radiation, that faint afterglow of the Big Bang, has an almost perfectly uniform temperature of about 2.7 degrees above absolute zero, no matter where we point our telescopes. In fact, its temperature is constant to within a few hundred thousandths of a degree. This seems reasonable at first glance until you realize the staggering implication. The universe simply hasn't existed long enough for light or any other influence to have traveled between these vastly separated regions to even them out. Imagine 2 cups of coffee placed in opposite corners of a gigantic cold room. If they are both exactly the same temperature down to a tiny fraction of a degree, you'd assume they had been in contact, that heat had flowed between them to reach equilibrium. But what if the room was so immense that there hadn't been enough time for any heat to travel from one cup to the other? You'd be left with a profound mystery. How did they coordinate their temperatures? This is precisely the situation with the cosmos. Take 2 points on opposite sides of the observable universe. Their light, emitted when the CMB was released just 380,000 years after the Big Bang, is only now reaching us after a journey of 13.8 billion years. But those 2 points themselves are separated from each other by a distance of over 90 billion light-years. They have been causally disconnected since the beginning of time. No information, no heat, no force could have possibly traveled from one to the other to smooth out their temperature differences. According to the standard Big Bang model without any additions, these regions should have evolved independently, developing wildly different temperatures and properties. The fact that they are identical to such an exquisite degree of precision is like finding identical snowflakes on 2 different continents that have never shared a weather system. It's a paradox that suggests the early universe was against all odds, somehow in perfect communication with itself. The solution that emerged to resolve this paradox is one of the most spectacular ideas in all of modern science: cosmic inflation. Proposed in the early 1980s by physicists like Alan Guth and Andre Linde, inflation posits that the universe underwent a breathtaking, exponential growth spurt in the very first fraction of a second of its existence. We're talking about a period from perhaps 10 to the power of -36 seconds to 10 to the power of -32 seconds after the initial singularity. In that almost immeasurably brief instant, the universe expanded by a factor of at least 10 to the power of 26. To put that incomprehensible rate into perspective, it's as if a subatomic particle suddenly ballooned to a size larger than our entire observable universe in a time span so short it makes a nanosecond look like an eternity. This superluminal expansion, faster than the speed of light, which is allowed because it's space itself stretching, would have taken a tiny, microscopic patch of the early cosmos that was already in thermal equilibrium and stretched it into the vast expanse we see today. All the regions we now see on opposite horizons were once crammed into this tiny, causally connected neighborhood, able to share heat and reach a uniform temperature before being violently ripped apart by inflation. The theory doesn't just solve the horizon problem, it also elegantly explains the origin of all cosmic structure. The quantum fluctuations that were present in that tiny seed were inflated to astronomical sizes, becoming the gravitational seeds for galaxies and clusters, the very tiny variations we now see in the CMB map. Yet, for all its majestic success, the inflationary paradigm comes with its own set of deep and troubling puzzles. The most profound of these is the measure problem, which emerges directly from the theory's most dramatic prediction: eternal inflation. The idea is that once inflation starts, it likely never completely stops. In most models, the inflattened field, the driver of the expansion, tunnels or rolls into its lowest energy state in some regions, creating what we call a pocket universe like our own, where inflation ends and a standard hot Big Bang begins. But in other regions, the field remains high, driving eternal exponential expansion. This process spawns an infinite fractal of pocket universes, a vast multiverse where every possible physical constant and law of physics is realized somewhere. This sounds like a fantastical conclusion, and it is. The measure problem asks a devastatingly simple question. If there are an infinite number of universes in the multiverse, how do we calculate the probability of anything? How do we determine what is likely and what is rare? In an infinite ensemble, everything that can happen does happen an infinite number of times. The concept of probability, the very foundation of scientific prediction, seems to break down. Why do we observe a universe with our specific, seemingly finely tuned constants? The inflationary multiverse might offer an explanation: everything exists, but it risks making cosmology untestable and unfalsifiable, a troubling prospect for a scientific theory. This has prompted some physicists to explore radical alternatives to inflation, theories that attempt to solve the horizon problem without invoking a multiverse. One of the most controversial is the idea of a variable speed of light, or Wiesel cosmology. Proposed by theorists like Joe Megiddo, this concept suggests that in the very early universe, the speed of light was not a constant, but was vastly higher than it is today. If light could travel infinitely fast in the first moments, then distant regions of the cosmos could have been in causal contact. Information could have zipped across the entire embryonic universe, homogenizing its temperature long before the speed of light settled down to its current finite value. This is a beautifully simple solution, but it comes at a great cost. It requires a direct modification of Einstein's theory of special relativity, one of the most rigorously tested pillars of modern physics. While intriguing, the lack of any experimental evidence for such a varying constant has kept Wiesel cosmology on the fringes of the field. another class of alternatives looks not to the beginning but to the end and then back to the beginning again. These are cyclic models of the universe, most notably Roger Penrose's conformal cyclic cosmology. In this breathtaking vision, the universe undergoes an endless sequence of cycles. It begins with a big bang, expands for eons, and eventually dissipates into a state of maximum entropy, a cold, dark, empty void populated only by low-energy photons. Penrose proposes that in this ultra-smooth, featureless state, the universe loses all sense of scale. It can be mathematically conformally rescaled to look exactly like the ultra-dense, ultra-hot state of a new Big Bang. In this model, the horizon problem is solved because the universe is infinitely old. The distant regions we see had an entire previous cosmic eon to interact and become uniform, and that smoothness is imprinted onto the next cycle. The large-scale uniformity we observe is not a feature of a beginning, but a relic of an ending, an echo of a universe that came before our own. It's a poetic and profound idea, though one that remains highly speculative and faces significant challenges in explaining the specific patterns we see in the CMB. Ultimately, the horizon problem is more than just a technical glitch in an old model. It is the anomaly that gave birth to our modern understanding of the cosmos. It forced us to conceive of inflation, a theory so powerful it now forms the bedrock of standard cosmology. Yet, in solving one profound mystery, it opened the door to others that are even more profound, questions about the nature of reality, the meaning of probability, and the possible existence of an infinite multiverse. The quest to understand why the universe looks the same in all directions has led us to the very precipice of scientific inquiry, to a place where our concepts of beginning and end, of what is unique and what is inevitable, are being fundamentally challenged. It stands as a testament to the power of a single, simple observation, the uniformity of the cosmic background, to reveal the deepest and most startling secrets of existence, proving that sometimes the most important questions are hidden in plain sight, written in the cold, ancient light that fills the void. What a breathtaking journey through the cosmos we have taken together. From the subtle, phantom tug on our own spacecraft in the solar system to the vast, coordinated river of entire galaxy clusters in dark flow, from the fleeting, perfect signal that shouted, "Wow!" into the void to the silent, overwhelming dominance of dark energy accelerating our universe toward a cold and lonely fate. Each of these 25 anomalies serves as a stark and humbling reminder. They are not merely curiosities or errors in our data. They are glaring signposts at the very edge of our understanding, each one pointing toward a fundamental truth. Our current map of reality is incomplete, and the universe is infinitely stranger and more wonderful than we have yet dared to imagine. Consider the profound implications of these mysteries. The flat rotation curves of galaxies forced us to invent an entirely new form of matter, a dark, invisible substance that shapes the cosmos yet remains utterly elusive to our detection. The Hubble-tension presents a direct conflict in our most basic measurement of cosmic expansion, suggesting that our standard model of cosmology, lambda CDM, might have a crucial piece missing, perhaps a new form of dark radiation or an evolution in dark energy itself. And then there is the sheer existential weirdness of quantum entanglement, a phenomenon that dissolves our classical notions of locality and suggests that the fabric of space-time itself may be an emergent illusion from a deeper, interconnected quantum reality. These are not small puzzles to be solved with a tweak to an equation. They are potential revolutions waiting to happen, each one holding the key to a new chapter in physics. What makes this so thrilling is that every single unexplained phenomenon represents a golden opportunity for a paradigm shift. The matter-antimatter asymmetry isn't just a question about the past. Its solution will reveal new fundamental forces or particles that operated in the universe's first second. The black hole information paradox is not an abstract puzzle. It is the central battleground in the war to unite general relativity with quantum mechanics, and its resolution will undoubtedly rewrite our understanding of space, time, and information. Even the controversial M-drive, though likely a measurement error, pushes our experimental rigor to its limits, training us to be better detectives for when a true anomaly emerges. Science does not progress by confirming what we already know, but by investigating what we cannot explain. These cosmic glitches are the universe's way of teaching us, of nudging us toward a grander, more complete theory of everything. We have wandered through a gallery of cosmic ghosts, from the missing baryons hiding in the warm, hot intergalactic medium to the hypothetical tetraneutron challenging the nuclear force itself. We have confronted the possibility that we live in a colossal supervoid, the KBC Void, and that our entire observable universe might bear the scar of a collision with another cosmos in the CMB cold spot. The sheer scale and diversity of these mysteries is what makes astronomy so perpetually captivating. There is always a deeper layer, a more profound question lurking just beyond the reach of our latest telescope or most powerful collider. Now we turn the conversation over to you. After this tour of the universe's greatest unsolved riddles, which one captivates your imagination the most? Does the eerie, one-time only nature of the wow signal fill you with a sense of cosmic wonder and loneliness? Or does the brutal, fundamental challenge of the vacuum catastrophe, that 120 order of magnitude error, strike you as the most humbling puzzle of all? Perhaps the sheer, counterintuitive magic of quantum entanglement boggles your mind, or the simple, haunting question of why we exist at all, thanks to the matter-antimatter asymmetry, resonates most deeply. Share your thoughts and favorite anomaly in the comments below. We are all students of the cosmos, and the discussion is where the real fun begins. If your curiosity is now burning brighter than a quasar, you are in the right place. This channel is dedicated to plunging into the deepest mysteries of space, time, and physics. We have more incredible journeys planned, exploring everything from the nature of consciousness to the possibility of simulated realities, all through the lens of cutting-edge science. To make sure you do not miss out, be sure to subscribe and hit the notification bell. The universe has countless more secrets to share, and together we will be here to uncover them, one mind-bending mystery at a time. Thank you for watching, and keep